Welcome to our channel. Long before dinosaurs roamed the Earth, our planet was an alien landscape teeming with unimaginable mysteries and terrifying conditions. Picture a realm where violent storms reshaped the land and massive volcanic eruptions spewed ash into the sky, creating an environment both hostile and dynamic. This was a time when life was still in its infancy, battling against the odds in a world that seemed hell-bent on eradicating it. Join us as we delve into the turbulent origins of Earth, charting its fiery beginnings and the gradual emergence of life from primordial chaos. We will explore the Paleozoic era, unearthing the incredible adaptations that allowed organisms to thrive in harsh environments, leading to breathtaking megafauna and dramatic extinction events. The formation of the Earth is a remarkable tale that dates back about 4.2 billion years. It began in the swirling chaos of our solar system, where dust and gas lingered in a vast cloud around the young sun. Over time, this cloud began to clump together under the force of gravity, creating larger bodies known as planetesimals, which collided and merged to form the Earth. In those early stages, the newly formed Earth was a violent and fiery place. The surface was molten, with temperatures soaring high enough to keep much of the planet in a state of liquid rock. Frequent collisions with other celestial objects added to the chaos, generating immense heat and leading to a volatile atmosphere filled with noxious gases. The landscape looked nothing like the Earth we know today. It was a landscape dominated by molten lava and toxic fumes. As time progressed, the planet began to cool. This cooling allowed a solid crust to form, providing a stable surface. Water vapor from the atmosphere started to condense, leading to the formation of the oceans. This transition marked a significant change in Earth's history, as the presence of water became essential for the development of life. The early oceans were likely not the clear blue waters we see today, but instead filled with minerals and chemicals, creating a rich environment for the eventual emergence of life. Throughout this fascinating process, the Earth continued to evolve, influenced by its interactions with the Moon, still forming planets, and its own geological activities. These events set the stage for a dynamic planet, one that would teem with life millions of years later. Surprisingly complex under the curtain of its tumultuous beginnings, the early Earth was not merely a barren rock. It was a thriving and evolving world, laying down the canvas for the story of life that would follow. Before life began to flourish on Earth, a variety of geological processes shaped the planet in profound ways. It all started around 4.5 billion years ago, when our planet formed from the dust and gas that surrounded the young sun. This period, known as the Hadean era, was marked by extreme volcanic activity. Intense heat from radioactive decay and constant meteorite impacts caused the surface to melt, creating a molten Earth. As the planet cooled, it began to solidify, forming its initial crust. Once a solid crust was established, tectonic activity took center stage. The Earth's lithosphere, which is the outer shell of the planet, started to break into plates that float on the semifluid asthenosphere beneath. These tectonic plates didn't just sit still. They moved, collided, and pulled apart, creating an ever-changing landscape. This movement led to the formation of mountains, ocean basins, and various geological features we recognize today, reshaping the planet's surface over millions of years. Another critical process during this time was erosion. Wind and water began to sculpt the land, wearing down rocks and transporting sediments. Rivers carved valleys, while glaciers ground down mountains, smoothing rough edges and depositing materials in new locations. This relentless flow of natural forces contributed to the formation of fertile plains and expansive river systems, setting the stage for future ecosystems that would eventually support life. In addition to these geological processes, the atmosphere also underwent significant transformations. Volcanic eruptions released gases that formed the early atmosphere. Although it was initially inhospitable to life as we know it, over time, as the planet stabilized, Conditions improved, leading to the appearance of water in liquid form and the establishment of vital environments. These primordial geological processes created the essential groundwork for the first living organisms, intertwining Earth's physical backdrop with the beginnings of life itself. The Earth's atmosphere has undergone a remarkable transformation since our planet first formed around 4.2 billion years ago. Initially, the atmosphere was likely composed of light gases, primarily hydrogen and helium, which are the most abundant elements in the universe. However, this early atmosphere was unstable and unable to support life. As the young Earth cooled, volcanic activity released gases such as water vapor, carbon dioxide, ammonia, and methane into the air, forming a secondary atmosphere. One of the most significant events in this atmospheric evolution was the cooling and condensation of water vapor, leading to the formation of oceans. These bodies of water not only helped to stabilize the climate, but also played a crucial role in chemical processes that are essential for life. Over millions of years, the oceans became a cradle for early life forms, creating conditions that would allow for biological evolution. Microbial life, particularly cyanobacteria, began to thrive, and through photosynthesis, they introduced oxygen into the atmosphere, fundamentally changing its composition. As these oxygen-producing microorganisms grew and spread, they slowly transformed the atmosphere from being rich in carbon dioxide to one that had a significantly increased concentration of oxygen. This pivotal moment is known as the Great Oxygenation Event, which occurred roughly 2.2 billion years ago. The rise in oxygen levels led to the extinction of many anaerobic organisms that could unsurvive in the new condition. But it also set the stage for the evolution of more complex life forms, including the first multicellular organisms. Over time, as life evolved and diversified, the atmosphere continued to change, influenced by both biological and geological processes. The balance of gases became more stable, supporting a wider variety of life forms. Eventually, this long process of evolution brought forth the rich and diverse ecosystems we see today, laying the foundation for everything from plants and animals to the breath of fresh air we enjoy. These early atmospheric changes were crucial, ensuring that Earth became a suitable home for life as we know it, allowing our planet to flourish in a vibrant web of existence. Meteorite impacts played a crucial role in shaping early Earth, acting as one of the primary forces during its formative years. Picture a young planet still cooling from its fiery birth, with a tumultuous surface marked by volcanic activity. Above this chaotic landscape, countless celestial bodies were on a collision course with Earth, sending large meteorites crashing down. These impacts not only contributed to the physical structure of our planet, but also had profound effects on its atmosphere and potential for supporting life. One of the significant outcomes of these impacts was the introduction of water and other essential elements necessary for life. Many scientists believe that some meteorites, particularly carbonaceous chondrites, contained ice, amino acids, and organic compounds. When they struck the Earth, they delivered these vital ingredients, providing a rich foundation for the development of life. In fact, it's theorized that some of the bodies striking Earth were responsible for creating large bodies of water, like oceans, which became the cradle for the earliest life forms. Moreover, these impacts contributed to the dramatic reshaping of the planet's surface. The craters left behind serve as testament to the violent history of Earth. Over millions of years, repeated impacts caused significant changes in geography and climate. The energy released from just a single large impact could have released enough heat to partially melt the crust, leading to the formation of new minerals and altering the landscape entirely. Yet, while these impacts could be devastating, they also fostered a dynamic environment that encouraged geological and biological evolution. The interplay between destruction and creation is a remarkable aspect of Earth's early development. From these cataclysmic events, our planet's conditions gradually evolved, setting the stage for the emergence of life and the rich diversity we witness today. In this way, meteorite impacts were not just random events. They were instrumental in shaping the very foundation of our planet and its capability to host life. The story of water on Earth begins billions of years ago, shortly after our planet formed about 4.5 billion years ago. The earliest evidence of water bodies is found in ancient rocks and minerals, particularly in regions of Canada and Greenland. These rocks contain isotopes of hydrogen and oxygen locked within them, which suggests that liquid water once existed on the surface. One of the key pieces of evidence comes from the study of zircon crystals, which are tiny mineral grains found in ancient sedimentary rocks. Some of the oldest zircon crystals, dating back around 4 billion years, have contained traces of water molecules. These findings imply that there were conditions suitable for liquid water and possibly even oceans. The presence of these crystals indicates that water was not just a fleeting phase, but an integral part of Earth's early geological history. But how did these early water bodies form? One theory suggests that water on Earth was delivered by cosmic sources, such as comets and asteroids. These celestial bodies, rich in ice, collided with the young Earth, releasing vast amounts of water vapor. Over time, as the planet cooled, this vapor condensed to form liquid water, leading to the development of the first oceans. Another contributing factor was volcanic activity. Early Earth's atmosphere, rich in gases, included significant amounts of water vapor, primarily from volcanic eruptions. As the Earth's temperature decreased, this water vapor condensed and fell as rain, contributing to the accumulation of water in basins that eventually became oceans. Together, these processes created conditions that allowed our planet to develop stable water bodies, setting the stage for the emergence of life and the complex ecosystems we see today. The origins of life on Earth are a fascinating topic that combines chemistry, geology, and even cosmic elements. The initial conditions necessary for life to begin were complex and varied, but several key factors played a pivotal role. One of the primary requirements was the presence of liquid water. Water is often referred to as a universal solvent, meaning it can dissolve a wide variety of substances, which is essential for the myriad of chemical reactions that underpin life. Scientists believe Earth had large bodies of water relatively early in its history, creating a conducive environment for biological processes to unfold. In addition to liquid water, the planet needed the right mix of chemical compounds. Essential elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur formed the building blocks of life as we know it. These elements could combine to form organic molecules, which are crucial for the development of more complex structures, such as proteins and nucleic acids. The right prebiotic chemistry had to occur, perhaps sparked by energy sources in the environment, such as lightning, volcanic activity, or the sun's radiation. The Earth's atmosphere was also a significant factor. Early in its formation, the atmosphere lacked oxygen and was rich in gases like methane, ammonia, and hydrogen. This reducing atmosphere would have enabled the formation of organic molecules through chemical reactions without the oxidative challenges that occur when oxygen is abundant. The famous Miller-Urey experiment in the 1950s demonstrated that simple organic compounds could form under such conditions, suggesting that the chemical pathway for life could occur naturally on a young Earth. Finally, stability and environmental conditions helped sustain the forming life. The planet's distance from the sun placed it in a habitable zone where temperatures allowed liquid water to exist. Geological activity could recycle nutrients and provide energy sources. Collectively, these initial conditions laid the groundwork for life's emergence, highlighting a beauty in the cosmic serendipity that allowed life to flourish in the cradle of our planet. Volcanic activity played a crucial role in shaping the primordial environments of our early Earth and potentially other planets. When Earth was still young, it was a hot and tumultuous place. Massive volcanic eruptions released an array of gases and particles into the atmosphere, creating conditions very different from what we see today. This activity contributed to the formation of new landforms and eventually set the stage for the development of life. The gases released during volcanic eruptions, such as carbon dioxide, water vapor, and ammonia, helped to build the early atmosphere. Initially, this atmosphere was likely thick and dense, shielding the surface from harsh cosmic radiation. Water vapor, a key component, eventually cooled and condensed to form oceans. These primordial seas became essential for the development of the first life forms, providing a stable environment rich in necessary chemicals. Moreover, volcanic activity contributed to the nutrient-rich environments needed for life to flourish. As volcanoes erupted and weathered, they released minerals that are vital for biological processes. These nutrients, carried by rain into the oceans, created a fertile habitat in which primitive organisms could arise. The cycle of volcanic eruptions and the subsequent weathering of volcanic rock created a dynamic interplay, nourishing the burgeoning ecosystems. Thus, volcanic activity was more than just a feature of geological interest. It was a foundational element in creating the conditions that allowed life to evolve. These processes set into motion the intricate balance of elements necessary for the development of complex organisms in a world that, much like our own today, was filled with both violent chaos and the promise of new beginnings. The origins of organic compounds on Earth, prior to the emergence of life, is a captivating topic that entices scientists and curious minds alike. Several theories have been proposed to explain how these essential building blocks, the very foundation of life, became present on our planet. One prominent idea is known as abiogenesis, which suggests that organic compounds formed from simple molecules in the presence of energy. This energy could have come from sources such as lightning strikes, volcanic activity, or even the sun's radiation. Another significant theory is the idea of extraterrestrial delivery, often referred to as panspermia. This hypothesis posits that organic compounds or even microbial life might have arrived on Earth embedded within comets, asteroids, or meteorites. Some experiments have shown that certain amino acids can survive the harsh conditions of space travel, raising intriguing possibilities about life's ingredients being distributed throughout the cosmos. Additionally, researchers have explored the role of hydrothermal vents on the ocean floor. These undersea environments, rich in minerals and heat, may have created the perfect condition for organic molecules to form. The combination of searing heat and the mixture of chemicals in water could have sparked the first steps toward life in these isolated, dark depths where sunlight cannot reach. Each of these theories highlights a unique pathway that organic compounds might have taken before life took root on our planet. The search for definitive answers continues, with every discovery opening new doors to understanding how life began in our universe. Each piece of the puzzle provides valuable insight into our origin story, inviting us to explore not just the past of Earth, but potentially of life itself across the universe. The early Earth was a turbulent place shaped by extreme weather patterns that were crucial for the development of prebiotic life. Large storms, intense temperatures, and fluctuating climates created a dynamic environment where chemical reactions could thrive. The energy released by storms, for instance, fueled processes that might have led to the formation of more complex organic molecules. These storms brought with them a variety of elements and compounds from the atmosphere and oceans, effectively mixing the primordial soup that scientists believe was essential for the emergence of life. Temperature fluctuations also played a vital role during this time. The planet experienced dramatic swings between hot and cold. Such variations can cause molecules to change state, promoting the interaction of different chemicals that might not ordinarily come into contact. For prebiotic compounds, these fluctuations provided the opportunity to form more complex structures, such as proteins and nucleic acids. Think of it as a cosmic mixing bowl, where the ingredients for life could be stirred together under the right conditions. Moreover, extreme weather conditions could have driven the formation of habitats like tidal pools or volcanic vents, where life could catalyze even further. These areas created stable microenvironments that sheltered emerging compounds. The highs and lows of weather systems might have also increased the variety of chemical reactions taking place, driving evolutionary processes even before true biological life began. Extreme weather patterns were not just destructive forces. They were integral to the chemical processes that gave rise to life on Earth. By providing the necessary energy, mixing resources, and fostering diverse habitats, these environmental conditions sculpted the foundations of biological complexity, setting the stage for life as we know it today. Before life emerged on our planet, Earth was a dynamic and noisy place in the vast theater of the cosmos. One of the most impactful events was the formation of the Moon, which occurred around 4.2 billion years ago. This event is typically attributed to a colossal collision between the early Earth and a Mars-sized body, often referred to as Theia. The debris from this collision eventually coalesced to form the Moon, which has played a crucial role in stabilizing Earth's axial tilt. This stabilization is vital for maintaining a relatively stable climate, which sets the stage for life to later develop. Another significant event was the bombardment of Earth by an array of asteroids and comets, especially during a period known as the Late Heavy Bombardment, which happened around 4 billion years ago. This period saw the Earth and other inner planets being pelted by thousands of celestial objects. While this bombardment was destructive, it also contributed crucially to the delivery of water and organic compounds that may have sparked the chemical processes necessary for life as beginnings. Water, a fundamental ingredient for all known life, was likely locked in those icy comets and asteroids. Additionally, the early atmosphere of Earth underwent dramatic changes due to volcanic activity and the release of gases like carbon dioxide, nitrogen, and sulfur dioxide. These gases created a thick atmosphere that could absorb harmful solar and cosmic radiation, providing a safer environment for potential life forms to emerge. The interplay of geological and astronomical factors during this time established Earth as a planet with the right conditions for life. Thus, while life as we know it did not exist during these periods, these astronomical events were crucially intertwined with Earth's evolution. They shaped not just the physical landscape and climate, but also laid the groundwork for the eventual rise of life, illustrating how our planet's fate was woven into the broader narrative of the cosmos. Before the reign of dinosaurs, the oceans teemed with a diverse array of life forms, many of which might astonish us today. These waters were home to myriad creatures, ranging from tiny plankton to massive predators, all existing within a complex and vibrant ecosystem. The oceans were dominated by life forms that have since evolved or disappeared entirely, revealing an extraordinary tapestry of ancient marine existence. Among the earliest and most prominent inhabitants were trilobites, which first appeared over 500 million years ago. These remarkable arthropods resembled modern-day horseshoe crabs and were abundant in various ocean habitats. They had a hard shell that provided protection, and some species grew quite large, reaching lengths of over a foot. Thanks to their extensive fossil record, trilobites offer crucial insight into the marine environments and ecological changes that occurred long before dinosaurs roamed the Earth. Another fascinating group of marine life was the mollusks, which included ancient relatives of modern snails, clams, and octopuses. Some of these creatures developed impressive shells that not only served as defense mechanisms, but also showcased beautiful patterns and intricate designs. Corals and sponges contributed to the physical structure of the seafloor, forming reefs and habitats for countless other marine species. This rich biodiversity created diverse ecological niches, stimulating evolution and adaptation throughout the ages. As we look back at these ancient oceans, it's essential to recognize that they were very different ecosystems compared to today. While we often think of the dinosaurs as the dominant life forms on land, the oceans were bustling with their own vibrant communities. The creatures that thrived in the seas laid the groundwork for the evolution of future life forms, including the fascinating marine animals we see today. Through understanding these earlier life forms, we gain a glimpse into the planet's history and the interconnectedness of all life across time. The story of life on Earth begins with simple organisms, which are often referred to as single-celled life. These tiny entities, such as bacteria and archaea, emerged over 3 billion years ago. They were the pioneers of evolution, capable of adapting to various environments and conditions. By living in extreme places like hot springs or deep-sea vents, they showcase the immense resilience of life. This adaptability sets the stage for more complex organisms to evolve. As these simple organisms thrived, they developed remarkable abilities, including photosynthesis and cellular respiration. Photosynthetic bacteria transformed sunlight into energy, releasing oxygen as a byproduct. This not only provided energy for themselves, but also led to the gradual accumulation of oxygen in the Earth's atmosphere. This process, known as the Great Oxidation Event, was a game changer, making the planet's conditions suitable for more complex life forms that relied on oxygen for survival. Around 1 billion years ago, complex cells, or eukaryotes, began to emerge. Unlike their simpler counterparts, these cells contained specialized structures called organelles. One group of eukaryotes eventually formed alliances with bacteria, leading to the development of plants and animals. This cooperation was crucial, as it allowed for greater complexity and specialization among living organisms, paving the way for diversity in shapes, sizes, and functions that we see today. The journey from simple to complex life is a testament to the power of evolution. It tells a story of survival, cooperation, and innovation. Each stage laid the foundation for the next, ultimately leading to vibrant ecosystems filled with a wide array of species, including humans. As we explore these ancient roots, we see how the persistence of simple life has helped shape the intricate tapestry of life on our planet. Microbial mats are fascinating structures that played a pivotal role in the early Earth's biosphere. These thick layers of microorganisms, particularly bacteria and archaea, provide insight into how life began and evolved on our planet. Composed mainly of single-celled organisms, microbial mats thrive in environments that are often extreme, such as hot springs, tidal flats, and other areas rich in nutrients. Their layered architecture showcases the interactions between different microbial communities, each occupying specific niches within the mat. The significance of these mats extends beyond their physical structure. They are believed to be some of the earliest forms of life, appearing over 3 billion years ago, during a time when the atmosphere lacked oxygen. These microbial communities engaged in processes such as photosynthesis and chemosynthesis. They produced organic matter and oxygen, gradually transforming the planet's atmosphere and paving the way for more complex organisms to evolve. Microbial mats were the architects of our early biosphere, setting the stage for the diverse life forms we observe today. Moreover, microbial mats contribute to biogeochemical cycles, influencing how elements like carbon, nitrogen, and sulfur circulate in the environment. By trapping sediments and nutrients, these mats create stabilized ecosystems that can last for thousands of years. They also reveal clues about past environments and climate conditions. Scientists study ancient microbial mats preserved in rocks to understand Earth's early history and the evolution of life. In recent times, researchers have rekindled interest in microbial mats, not just for their historical significance, but also for their potential applications in modern science and technology. They are being examined for their contributions to biotechnology, including waste management and biofuel production. The resilience and adaptability of these ancient microorganisms continue to inspire exploration and innovation in various fields, proving that even the simplest forms of life hold immense importance in the grand story of our planet. Cyanobacteria, tiny blue-green microorganisms, played a pivotal role in transforming the Earth's atmosphere over 2 billion years ago. These remarkable organisms were among the first photosynthetic life forms, harnessing the energy from sunlight to drive their growth. Through the process of photosynthesis, they took in carbon dioxide and released oxygen as a byproduct. This simple act set off a chain reaction that altered our planet's environment in profound ways. Initially, Earth's atmosphere was largely composed of nitrogen, carbon dioxide, and other gases, with very little oxygen. But as cyanobacteria proliferated in oceans and other water bodies, they began to spew oxygen into the atmosphere in increasing amounts. Over millions of years, this oxygen accumulated, leading to the Great Oxidation Event. This dramatic shift not only changed the composition of the atmosphere, but also laid the groundwork for the evolution of complex life. The rising levels of oxygen had significant consequences for Earth's ecosystems. Many organisms that thrived in the low oxygen environment could not survive in the new conditions, leading to mass extinctions. However, the oxygen-rich atmosphere paved the way for aerobic organisms, those that use oxygen for respiration. This set the stage for the emergence of diverse life forms, including plants, animals, and ultimately humans. Cyanobacteria were not just early inhabitants of the Earth. They were transformative agents that reshaped the atmosphere, fostering a thriving and diverse biosphere. Their legacy is woven into the very fabric of life on our planet today, illustrating how microorganisms can catalyze monumental changes in the environment. Fossil records serve as time capsules, offering a glimpse into the ancient past and revealing details about the first life forms that inhabited our planet. These records are primarily composed of mineralized remains or traces of organisms that lived millions, even billions of years ago. The earliest fossils, which date back around 3.5 billion years, provide key insights into the nature and complexity of life's beginnings. Among the most intriguing findings are stromatolites, layered structures formed by the activities of ancient microorganisms, primarily cyanobacteria. These remarkable fossils showcase how these simple life forms thrived in Earth's early oceans, harnessing sunlight through photosynthesis and producing oxygen as a byproduct. The emergence of oxygen in the atmosphere, made possible by these tiny organisms, played a crucial role in shaping the planet's environment and set the stage for more complex life forms to evolve. In addition to microbial life, fossil records reveal that some of the first larger organisms were soft-bodied creatures, often poorly preserved due to their delicate structures. The Cambrian explosion, approximately 540 million years ago, marks a significant milestone in the fossil record, showcasing a rapid diversification of marine life. This event illustrates how simple cellular organisms evolved into a myriad of complex life forms, including early ancestors of modern animals. Through the lens of fossil records, we can piece together the evolutionary narrative of our planet. They highlight not only the resilience of life in adapting to changing conditions over eons, but also the interconnectedness of all living things. By examining these ancient remnants, scientists continue to uncover the story of life's origins, offering a sense of wonder about how far we have come since those first simple cells took shape in a primordial world. The Paleozoic era, which spanned from about 548 million to 250 million years ago, was a transformative period in Earth's history. This era witnessed the emergence of complex life forms and the establishment of land environments, radically changing the planet as we know it. The Paleozoic can be divided into several periods, each marked by significant evolutionary milestones that shaped terrestrial landscapes. During the early Paleozoic, particularly in the Cambrian and Ordovician periods, marine life flourished. This period laid down the foundational ecosystems in the oceans. However, it was during the Silurian period that significant changes began to occur on land. The first plants, simple mosses and liverworts, emerged from the oceans, taking root in the soil. These pioneering plants played crucial roles in stabilizing the ground and creating conditions for further ecological diversity. As we move into the Devonian period, often referred to as the Age of Fish, the terrestrial environment underwent another leap forward. More complex plants evolved, such as the first trees and vascular plants, which would dominate land ecosystems for millions of years. These developments led to the formation of lush forests that drastically changed the atmosphere by increasing oxygen levels, which in turn supported the rise of even more sophisticated life forms, including the first land animals like insects and amphibians. By the late Paleozoic, particularly in the Carboniferous period, extensive swampy forests became prevalent. These lush environments eventually contributed to vast coal deposits we rely on today. The Paleozoic era thus set the stage for the rich tapestry of life and landscapes we see in the modern world. It was a time of remarkable evolution and environment building that provided the framework for the complex ecosystems we cherish now. The Cambrian explosion, a remarkable period in Earth's history, marks the time when life on our planet experienced a rapid and dramatic diversification. Spanning from approximately 548 million to 538 million years ago, this era showcases a transition from simple unicellular organisms to complex multicellular life. It's considered one of the most significant evolutionary events, laying the foundation for many modern animal groups. Among the major highlights of the Cambrian explosion is the sudden appearance of various body plans. Prior to this period, most life forms were simple and soft-bodied, such as algae and small single-celled organisms. However, during the Cambrian, we see the emergence of complex forms, including the first representatives of most animal phyla, which are groups of animals sharing a common structural organization. For example, creatures like trilobites, arthropods, and early mollusks began to populate the oceans, each exhibiting unique adaptations and features. Another significant event was the development of hard body parts, such as shells and exoskeletons. This innovation provided not only protection against predators, but also paved the way for new ecological dynamics. The fossil record from this time reveals a wealth of organisms with intricate structures, showcasing an explosion of creativity in nature. The presence of these hard parts also aids paleontologists today, as they preserve better and offer insights into the ancient marine ecosystems. The Cambrian explosion was also a time of competitive interactions among species. With the arrival of more complex life forms, predation emerged as a crucial driving force in evolution. Organisms began to develop defense mechanisms, such as hard shells or the ability to burrow into the seafloor. This interplay of predator and prey led to a dynamic evolutionary landscape. The aftermath of the Cambrian laid the groundwork for future diversification, setting the stage not only for the complexity of life we see today, but also for the ecosystems that would arise in subsequent geological periods. The Paleozoic era, spanning from about 548 million years ago to 250 million years ago, marks a remarkable chapter in the story of life on Earth, particularly in the evolution of plant life. This era witnessed a transformation from simple aquatic plants to complex land-dwelling organisms. Early in the Paleozoic, during the Cambrian period, the dominant plant forms were simple algae, floating or clinging to the ocean floor. These primitive life forms began the long journey towards the diverse range of plant species we see today. As we move into the Ordovician and Silurian periods, significant advancements occurred. The first vascular plants emerged, allowing them to grow taller and develop extensive root systems. These adaptations greatly enhanced their ability to access nutrients and water. The development of true leaves and the ability to reproduce using spores enabled these plants to colonize land more effectively. This pioneering plant life not only began to reshape the terrestrial landscape, but also paved the way for other organisms by creating new habitats. The Devonian period, often referred to as the Age of Fishes, was also a pivotal time for plant evolution. It was during this era that significant diversification occurred, with the appearance of the first trees and the formation of extensive forests. Large woody plants emerged, stabilizing the soil and fostering an entirely new ecosystem. The dense foliage and complex root systems played a crucial role in reducing erosion and promoting soil formation. These early forests would later influence global climate patterns by contributing to atmospheric oxygen levels. By the end of the Paleozoic, specifically in the Carboniferous period, the planet experienced lush, swampy environments dominated by giant ferns and seed plants. This proliferation of plant life not only altered terrestrial habitats dramatically, but also set the stage for future evolution. The increased biodiversity created numerous niches for insects and other organisms, essentially laying the groundwork for modern terrestrial ecosystems. The legacy of these ancient plants continues to echo through today's vast forests and grasslands, reminding us of the profound impact life on land has had on our planet's history. The Devonian period, which spanned from around 430 million to 360 million years ago, is often referred to as the Age of Fishes. This title reflects the remarkable diversity and dominance of fish during this era. During the Devonian, the oceans were teeming with an array of fish species, including early ancestors of modern-day sharks and bony fish. These creatures flourished in the marine environments of the time. In addition to the jawed fish that emerged, there were also a variety of jawless fish. Among the most notable were the armored fish known as placoderms. These fish were heavily plated and could be quite large, showcasing evolutionary advancements in both size and complexity. The period also saw the rise of lobe-finned fish, which eventually gave rise to the first land-dwelling vertebrates. This evolutionary transition is crucial, as it sets the stage for the colonization of land by vertebrates in the following periods. However, fish were not the only prominent life forms during the Devonian. This era also gave rise to the first trees and complex plant life on land. The appearance of these early land plants played a critical role in reshaping the environment and contributed to significant changes in climate and soil. This transition catalyzed a symbiotic relationship between terrestrial ecosystems and aquatic life, influencing both environments. As we reflect on the Devonian period, we can appreciate not just the Age of Fishes, but also the pivotal developments that took place in both marine and terrestrial realms. The evolutionary innovations during this time laid the groundwork for life as we know it, making it a truly transformative period in Earth's history. The Carboniferous period, which spanned from about 360 million to 300 million years ago, was a time of remarkable evolutionary developments, particularly in the realm of plants and insects. This era witnessed the establishment of extensive forests dominated by towering trees, ferns, and seedless vascular plants, which significantly altered the planet's landscape and atmosphere. As these plants flourished, they played a crucial role in producing oxygen, enriching the Earth's air, and allowing for the evolution of complex life forms. One of the most striking advancements during this period was the emergence of the first true amphibians. These creatures evolved from lungfish ancestors and marked a pivotal transition from life in water to life on land. Amphibians showcased adaptations such as limbs capable of supporting their weight on solid ground and lungs for breathing air, thus laying the foundation for the eventual rise of reptiles and later mammals and birds. This shift to terrestrial life was a defining moment in the history of evolution, highlighting the adaptability of life forms in response to changing environments. In addition to amphibians, the Carboniferous period also saw a significant increase in the diversity and size of insects. The warm, humid climate and abundant vegetation created an ideal habitat for these creatures to thrive. Some of the largest insects ever to exist, like dragonflies with wingspans of up to 2 feet, roamed the skies, aided by the high oxygen levels produced by dense forests. This evolutionary trend not only showcased the versatility of insects, but also illustrated their crucial role in pollination and the overall ecosystem balance. The Carboniferous was indeed a time of transformation, setting the stage for future evolutionary developments. The advancements seen during this period were not merely adaptations to survive, but were key innovations that changed the course of life on Earth. The legacy of the plants and animals that emerged during this time still resonates today, as they help shape the ecosystems that support the diverse life forms we see in our modern world. Such milestones remind us of the intricate tapestry of evolution that continues to unfold. The transition from water to land marked a pivotal moment in the evolution of animals. This monumental change began over 300 million years ago, when certain fish ventured onto land, driven by the search for new habitats and feeding opportunities. Adapting to life outside the water demanded significant physiological and anatomical changes, allowing these creatures to thrive in a completely new environment. One of the most critical adaptations involved the development of lungs. Early land-dwelling creatures transformed their gills, which were effective for extracting oxygen from water, into systems that could extract oxygen from the air. This adaptation enabled them to breathe efficiently in a terrestrial setting. Furthermore, their bodies began to evolve support structures to combat the pull of gravity, which is much more pronounced outside water. The limbs of these animals became sturdier and evolved from the fins of their aquatic ancestors, allowing them to move effectively on land. The shift to a terrestrial lifestyle also influenced their reproduction. Many aquatic species lay eggs in water, but on land, the risk of desiccation or drying out became a concern. To address this, some species developed amniotic eggs, a crucial innovation that encapsulated the developing embryo in a protective shell. This advancement not only enhanced their ability to reproduce on land, but also paved the way for the emergence of reptiles and, eventually, mammals. This transition fundamentally reshaped ecosystems, leading to the rise of various vertebrate groups. The diversity that emerged from these early land animals includes everything from amphibians to reptiles, birds, and mammals. The move from water to land did not just change where animals lived. It initiated a complex web of evolutionary pressures that molded life into the forms we recognize today, making it a significant chapter in the story of life's evolution on Earth. Early amphibians emerged from their aquatic ancestors during a significant evolutionary transition, approximately 360 million years ago. This shift from water to land required a series of remarkable adaptations that enabled them to thrive in a new environment. One of the most crucial changes was the development of limbs. Unlike their fish relatives, amphibians evolved sturdy, bony limbs that allowed them to support their bodies on dry land and move effectively across various terrains. Another adaptation involved the respiratory system. While fish used gills to extract oxygen from water, early amphibians developed lungs, which enabled them to breathe air. However, they retained some reliance on their skin for respiration. The skin of amphibians became more permeable, allowing them to absorb oxygen directly from the atmosphere. But this also meant they needed to keep their skin moist to prevent dehydration. This dual system of respiration was essential for their survival in a terrestrial habitat. Reproductive changes were also vital. Most amphibians lay their eggs in water to prevent desiccation, but early forms began developing behaviors that allowed them to seek out moist environments. This adaptability helped ensure that their eggs would not dry out before hatching. Additionally, protective adaptations, like a gelatinous coating around the eggs, provided further safety against environmental threats, bolstering the chances of successful reproduction. Finally, their sensory systems adapted to help them navigate the complexities of land. Early amphibians developed more refined sight and hearing abilities to respond effectively to the challenges of a terrestrial ecosystem. With these adaptations, they were able to exploit new ecological niches, significantly diversifying and laying the groundwork for the multitude of amphibian species we see today. This transformation, rooted in evolutionary ingenuity, marked a pivotal moment in the history of life on Earth. The formation of supercontinents, such as Pangaea, had a profound impact on biodiversity across the planet. When these massive land masses emerged from the ocean, they created new environments and altered existing habitats. As continents merged, species that once thrived in isolation were brought together, allowing for greater genetic exchange among populations. This commingling often led to the emergence of new species as different plants and animals adapted to their new neighbors. However, the consolidation of land also posed challenges. The unification of continents meant that certain habitats, particularly those that were once separated by oceans, became homogenized. As a result, the unique species that had developed in isolated ecosystems started to face competition from newcomers. This could result in some species thriving, while others face extinction, leading to shifts in biodiversity on a large scale. Additionally, the formation of supercontinents affected climatic patterns. With larger land masses, the distribution of sunlight and moisture changed significantly, creating arid regions and altering rainfall patterns. These changes in climate could lead to the decline of certain ecosystems and the rise of others, reshaping the tapestry of life on Earth. Species had to migrate, adapt, or face the threat of extinction in response to these new environmental pressures. Ultimately, while the merging of continents brought about exciting opportunities for species interaction and diversification, it also introduced competition and extinction pressures that have shaped the biodiversity we see today. The story of supercontinents is one of dynamic change, illustrating the intricate relationship between planetary geologic processes and the life forms they influence. When early organisms took their first steps onto land, they encountered a range of significant challenges that tested their adaptability and resilience. One of the primary issues was desiccation, or drying out. Unlike their aquatic ancestors, organisms on land were exposed to the sun's harsh rays and the air, which could sap moisture quickly. This necessitated the evolution of protective features, like thickened skin or outer coatings, to retain water and prevent dehydration. Another formidable challenge was the need for structural support. In water, buoyancy provides an effective counterbalance against gravity. However, on land, organisms had to develop sturdy structures to avoid collapse. Early plants adapted by developing cell walls reinforced with lignin, allowing them to stand upright and reach toward sunlight. Similarly, early arthropods evolved exoskeletons that provided both support and protection against predators, marking a significant step in their adaptation to terrestrial life. Temperature regulation also posed problems for these early land dwellers. Unlike the relatively stable temperatures of aquatic environments, terrestrial environments could be extreme, with hot days and cold nights. Early organisms had to find innovative solutions, such as burrowing to escape extreme temperatures or evolving behavioral changes, like seeking shade during the hottest parts of the day. Lastly, the increased complexity of terrestrial ecosystems presented new challenges. Organisms had to deal with navigating different habitats, finding food, and avoiding predation, all in a more diverse environment than the ocean. The interaction with other species, whether as competitors or predators, demanded rapid evolution and adaptation. Together, these challenges shaped the course of life on land, leading to the diverse array of terrestrial ecosystems we see today. The transition of life from oceans to land was a monumental shift in the history of our planet, and two driving forces behind this evolution were predation and competition. As early creatures crawled out of water, they faced entirely new challenges and opportunities in their terrestrial environments. Predation, in particular, acted as a significant catalyst for evolution. Creatures that adapted quickly found ways to avoid becoming prey, while others developed traits that helped them become more effective hunters. In the early stages of terrestrial life, competition for resources was fierce. Plants and animals had to contend not only with each other, but also with the elements. Phototrophic plants began to emerge, claiming sunlight, while insects and other creatures competed for food sources. Those that could effectively gather resources tended to thrive, driving the rapid evolution of body structures and feeding strategies. The emergence of different niches in these habitats led to a dazzling variety of life forms, each uniquely equipped to survive in its environment. Moreover, as predators evolved more sophisticated hunting techniques, potential prey species developed their own strategies to escape. This dynamic led to what's known as an evolutionary arms race. For instance, some early land animals evolved faster limbs to outrun predators, while others developed better camouflage to remain hidden. These adaptations fostered a diverse range of evolutionary strategies, leading to the incredible biodiversity we see today. In conclusion, predation and competition acted as twin forces in shaping the early ecosystems on land. They fostered a relentless drive for adaptation that not only helped organisms survive, but also allowed them to carve out their own unique paths in the intricate web of life. This evolutionary dance continues to resonate through the ages, influencing the direction of life on Earth. The end of the Paleozoic era, which occurred around 250 million years ago, is marked by one of the most significant mass extinction events in Earth's history, often referred to as the Permian-Triassic extinction. This event claimed the lives of approximately 95% of marine species and 70% of terrestrial vertebrate species. The evidence for such a dramatic decline in biodiversity is abundant and varies across multiple scientific disciplines. Fossil records provide some of the clearest insights into this extinction event. Geologists have discovered layers of sediment that correspond to the end of the Paleozoic, known as the Permian period. Within these layers, there is a stark reduction in the diversity of fossilized remains. Species that once flourished, such as many types of coral and certain trilobite species, virtually disappeared. This drastic drop in biodiversity indicates a catastrophic event that reshaped life on Earth. Alongside fossil evidence, geochemical data points to significant environmental changes during this period. Scientists have found elevated levels of carbon dioxide and other greenhouse gases in rocks dating to this time. Such an increase likely contributed to global warming, altering habitats dramatically. Additionally, researchers have examined isotopic signatures that signify widespread anoxia, or lack of oxygen, in ocean waters, which would have been fatal for many marine creatures. Finally, evidence of major volcanic activity has emerged from this period. Massive volcanic eruptions in what is now Siberia released enormous amounts of ash and gases into the atmosphere. This phenomenon, known as the Siberian traps, would have led to climate shifts and contributed significantly to the ecological collapse. The combination of fossil records, geochemical signs of environmental change, and the impacts of volcanic activity creates a compelling narrative of how multiple factors converged to cause one of the Earth's most profound extinction events. The Permian-Triassic extinction event, often referred to as the Great Dying, occurred about 250 million years ago and is recognized as the most significant mass extinction in Earth's history. This cataclysmic event led to the loss of approximately 95% of the planet's marine species and around 70% of terrestrial species. It was caused by a combination of volcanic activity, methane releases, and climate changes, which devastated ecosystems and the conditions needed for life to thrive. However, amidst this profound destruction, the Permian-Triassic extinction event also set the stage for a remarkable rebirth. With so many species gone, ecological niches were opened, allowing new organisms to emerge. The aftermath of the extinction allowed survivors, like certain reptiles and the ancestors of mammals, to expand into new environments. Over time, these organisms began to evolve into new forms adapted to changing ecosystems. In the Triassic period, which followed the extinction, life took on vibrant new shapes. The relatively empty ecological spaces fostered diversification. For instance, early dinosaurs began their dominance, while many plants adapted to the new climate, leading to unprecedented variety in both flora and fauna. This wave of evolution laid the groundwork for the ecosystems we recognize today, initiating the rise of more complex life forms and ecosystems. Ultimately, the Permian-Triassic extinction serves as a powerful reminder of life's resilience. From the ashes of devastation, evolution continued its relentless intrigue, producing an array of astonishing species that shaped the trajectory of life on Earth. This event underscores the ever-adaptive nature of life, showcasing how, through disaster, new opportunities can arise for the flourishing of different life forms. The end of the Permian period, roughly 250 million years ago, is often referred to as the world's largest mass extinction, claiming around 93% of marine species and 77% of terrestrial species. This period of sudden, catastrophic environmental change has been attributed to a combination of factors that reshaped Earth's ecosystems. One significant contributor was volcanic activity, particularly in what is now known as Siberia. This immense release of lava, known as the Siberian Traps, released vast amounts of carbon dioxide and sulfur dioxide into the atmosphere. This influx of greenhouse gases likely triggered dramatic climate shifts, leading to a rise in global temperatures and a change in precipitation patterns, which drastically affected habitats and species survival. Additionally, the oceans faced dire consequences. The excessive carbon dioxide contributed to ocean acidification, which harmed marine life, particularly organisms with calcium carbonate shells. Balanced ecosystems teetered on the verge of collapse as the food chain unraveled, pushing many species toward extinction. Finally, shifting continents played a role. During the late Permian, the Earth's land masses were converging into a single supercontinent called Pangaea. This massive land configuration altered ocean currents and climate systems, leading to arid conditions in many areas and affecting the distribution of flora and fauna. Together, these factors intertwined to create a perfect storm of environmental upheaval, culminating in one of the most significant extinction events in Earth's history. Throughout Earth's history, extinction events have played a pivotal role in shaping the course of evolution. These dramatic moments, where a significant number of species die out in a relatively short span, often clear the way for new life forms to emerge and thrive. The most famous of these events is the mass extinction that occurred about 66 million years ago, marking the end of the age of dinosaurs. This catastrophic event opened ecological niches that mammals, once small and hidden, could fill and adapt to, leading to the diverse range of species we see today. Interestingly, these extinction events often result from a combination of factors, including environmental changes, volcanic activity, and even asteroid impacts. Take the Permian-Triassic extinction, which occurred nearly 300 million years ago, often referred to as the Great Dying. It wiped out around 95% of all species on Earth. The aftermath of such a significant loss led to the rise of reptiles and eventually the dinosaurs, showcasing how survival following these calamities can kickstart new evolutionary paths. Furthermore, extinction events tend to cause a surge in evolutionary innovation. With many competitors gone, the surviving species often evolve rapidly to explore a range of new adaptive strategies. This phenomenon, referred to as adaptive radiation, has resulted in the extraordinary diversification of life forms. For example, after the dinosaurs vanished, mammals underwent an explosive evolution, leading to the many forms we see today, from the majestic blue whale to the tiny bumblebee. While extinction might seem like a foreboding end, it often serves as a foundation for new beginnings. These cycles of life and death remind us that the history of Earth is one of constant change and adaptation, where each loss paves the way for future biodiversity and resilience. Thus, by examining how extinction events have shaped evolution, we gain a deeper appreciation for the intricate tapestry of life that continues to evolve on our planet. Throughout Earth's history, there have been several extinction events that dramatically reshaped the planet's ecosystems. One of the most significant was the Permian-Triassic extinction event, which occurred around 250 million years ago. This event alone wiped out about 90% of all marine species and 75% of terrestrial life. The vast majority of Earth's biodiversity was lost, creating an opportunity for new forms of life to evolve and thrive in the aftermath. Following this mass extinction, the Triassic period emerged as a time of recovery and adaptation. The landscapes were vastly changed, and new ecosystems began to take shape. Among the survivors were early reptiles, who brought resilience and adaptability to the new environments. These reptiles were the precursors to the dinosaurs, setting the stage for their eventual dominance. In this period of evolutionary experimentation, species that we now recognize as the ancestors of dinosaurs started to diversify. As time progressed into the Jurassic period, the Earth saw warm climates and the opening of new ecological niches. This was crucial for the expanding population of dinosaurs, as they adapted to a variety of environments, from lush forests to arid deserts. Earlier extinction events functioned like a reset button for life on Earth. By eliminating dominant species, they allowed more adaptable forms of life, like the dinosaurs, to flourish in their wake. The amazing diversity of life we now see owes much to those tumultuous periods in our planet as history. Each extinction event played a pivotal role in shaping the path of evolution, leading eventually to the age of dinosaurs, a truly remarkable chapter in the story of life on Earth. Long before the age of dinosaurs took center stage in Earth's history, the planet was home to an array of remarkable land animals. Among the giants of this era were the ancestors of today's mammals, specifically the formidable synapsids. These creatures roamed the Earth during the late Paleozoic era and into the early Mesozoic. Some of the largest land animals included the Gorgonopsids, which were predatory synapsids that could grow as large as a modern-day lion, and the Dicynodonts, herbivorous animals that could reach the size of a rhinoceros. One notable adaptation of these early giants was their powerful jaw structure. Gorgonopsids, for instance, evolved elongated canine teeth, allowing them to grasp and tear into their prey effectively. Their adaptations also included a more efficient respiratory system compared to earlier reptiles, which supported their larger size and more active lifestyle. This allowed them to maintain a higher metabolic rate, giving them an advantage in both hunting and evading predators. In a different vein, the Dicynodonts showcased impressive evolutionary traits of their own. They developed strong, beaked jaws ideal for processing tough plant material, enabling them to thrive in diverse environments. Their body sizes and shapes varied, but many exhibited a stocky build with sturdy limbs designed for supporting their substantial weight as they grazed across the prehistoric landscape. These adaptations highlight a crucial point in evolutionary history, illustrating how the quest for survival shaped the physiology of these ancient creatures. Although these magnificent synapsids eventually fell into extinction, their evolutionary legacy paved the way for the fascinating diversity we observe in mammals today. The extraordinary adaptations of these prehistoric giants remind us that Earth's history is not just a story of dinosaurs, but also of a diverse array of life that set the groundwork for the creatures that came after. Throughout the history of life on Earth, competition among species has played a pivotal role in shaping the unique characteristics we observe in megafauna. Megafauna refers to large animals, typically weighing over 100 pounds, that evolved in various ecosystems across the globe. As these species competed for resources such as food, water, and territory, they gradually developed special traits to thrive in their environments. For instance, consider the woolly mammoth. This massive creature adapted to harsh, cold climates with its thick fur and a layer of fat beneath its skin. Such adaptations were not only advantageous, but necessary for survival, as it competed with other herbivores for vegetation. The presence of other large mammals, like the saber-toothed cat, also influenced the mammoth's evolution. Competition for prey led to both species refining their hunting and grazing strategies, resulting in unique physical traits suited to their ecological niches. Similarly, in the prehistoric era of giant reptiles, competition shaped the development of traits in creatures like the giant ground sloth. These enormous herbivores evolved long limbs and powerful claws, which helped them reach high branches for food, while also defending against predators. The interplay of competition pushed these animals to adapt, leading to the evolution of specialized features that would help them succeed in their environments. This dynamic of competition continues to play a crucial role even in modern ecosystems. While today's megafauna may look different than their ancient relatives, the struggle for survival has led to the distinctive traits we observe today. This intricate dance of competition and adaptation has crafted a rich tapestry of life on Earth, showcasing the endless possibilities of evolution driven by the need to survive and thrive. In the vast stretches of prehistoric Earth, ecosystems thrived in ways that were astonishingly diverse and complex. During the age of dinosaurs, which spanned over 150 million years, the planet was awash with life that has captured our imagination. These ecosystems were not only vibrant, but also critical in supporting enormous creatures like the massive herbivores, the towering sauropods, and the fierce carnivores famously known as theropods. Forests dominated many regions, with giant ferns, cycads, and conifers providing both shelter and food. These were not the leafy trees we know today. Rather, they had thick trunks, sweeping branches, and canopies that stretched high into the sky. The underbrush was filled with a variety of plants that evolved to thrive in the dappled light filtering through the tall trees. This environment created a rich habitat that sustained not only dinosaurs, but also a myriad of smaller creatures, including mammals, birds, and insects, which played vital roles in this ancient world. In addition to forested regions, vast plains and wetlands existed too. These areas were crucial for the growth of flowering plants and grasses, which formed the foundation of complex food webs. Large herbivores would graze on these plants, and their sheer size helped shape the landscape as they navigated their territories. The presence of these enormous animals influenced the distribution of plant life, promoting a dynamic relationship between flora and fauna. Finally, water bodies such as rivers, lakes, and coastal areas added another layer of richness to these ecosystems. They attracted diverse life forms, supporting fish, amphibians, and the early ancestors of modern reptiles. Such variety ensured that prehistoric ecosystems were bustling with activity, offering resources, habitats, and nourishment to large creatures and small alike. Taken together, these ecosystems were marvelously interconnected, creating a world where life flourished in extraordinary forms, capturing our fascination and exploration even millions of years later. The survival of prehistoric megafauna, which includes the massive creatures that roamed the Earth during the Pleistocene epoch, was significantly influenced by climate change. As glaciers advanced and retreated, the ecosystems in which these animals lived underwent dramatic transformations. During cold periods, also known as glacial periods, expansive grasslands and tundra environments flourished, providing ample grazing opportunities for large herbivores like woolly mammoths and giant ground sloths. However, as the climate warmed in between these glacial periods, the habitats that supported megafauna began to shrink. The rise in temperatures led to the expansion of forests and a shift in vegetation, which profoundly impacted the availability of food for these enormous animals. Many species adapted to the cold, open landscapes found it increasingly difficult to survive in the denser, warmer ecosystems that emerged. This change in climate and habitat was a significant factor that challenged their survival. Additionally, human activity during this time played a crucial role in the fate of megafauna. As the climate warmed, humans began expanding their territories and hunting practices. The combination of hunting pressure and habitat change created a double threat to these large animals. Many species could not cope with this newfound pressure, leading to widespread extinction events toward the end of the last ice age. In conclusion, climate change profoundly affected the megafauna by altering their habitats and food sources, while simultaneously increasing human interactions. This complex interplay between changing climates and the rise of human populations ultimately shifted the course of these giant creatures, leading many to extinction and reshaping the ecosystems we see today. The story of megafauna illustrates the delicate balance between climate and life, a balance that remains relevant as we confront the challenges of climate change in our own time. The fossil record is a fascinating window into the past, revealing the existence of countless creatures that once roamed our planet. Fossils are the preserved remains or traces of organisms, and they can take many forms, from bones and teeth to footprints and even impressions of soft tissues. By studying these remnants, paleontologists can piece together clues about ancient life, its evolution, and the environments in which these creatures lived. One of the most compelling aspects of the fossil record is its ability to document changes over time. For example, the discovery of dinosaur fossils in different layers of sedimentary rock allows scientists to establish a timeline of when these creatures lived. This stratification helps researchers understand not only the types of species that existed, but also how they adapted to changing climates and ecosystems over millions of years. The transitions between different fossil layers often signal significant biological events, such as mass extinctions or the emergence of new species. Additionally, innovations in technology have enhanced our ability to analyze fossils. Techniques like carbon dating and imaging allow scientists to determine the age of fossils more accurately and to visualize their internal structure. This has led to exciting discoveries that shed light on previously unknown species and evolutionary paths. Every fossil unearthed adds another piece to the puzzle, enriching our understanding of the complex web of life that has existed on Earth. Careful study and interpretation of these ancient remains, we uncover a story that informs us not only about the creatures themselves, but also about the planet's history. This ongoing research bridges the gap between the past and present, helping us appreciate the diversity of life and the processes that shape our world today. Fossils are more than mere relics. They are vital records of life that persist to stimulate our curiosity and deepen our knowledge of life as grand narrative. Long before dinosaurs roamed the Earth, the planet experienced significant climate fluctuations that dramatically shaped its geological and biological landscapes. These changes, driven by various factors such as volcanic activity, continental drift, and variations in radiation, initiated a series of ecological and geological transformations that altered the course of life. During the periods of severe cooling, known as ice ages, a planet's temperatures dropped, causing glaciers to expand across vast land masses. These icy sheets not only changed the surface of the Earth, but also influenced global sea levels and ocean currents. As glaciers melted, they carved out valleys and created new landforms, while rising sea levels flooded coastal areas, leading to the creation of shallow seas rich in nutrients. These shallow marine environments became hotspots for life and set the stage for the evolution of diverse aquatic ecosystems. Conversely, warmer periods resulted in lush tropical landscapes. Giant ferns and towering conifers flourished, creating rich forests. This diverse flora provided habitats for emerging species, including early reptiles and amphibians. The interplay of climate and geography led to an increase in biodiversity, enabling a variety of life forms to adapt to changing conditions. The development of different ecosystems was crucial for nurturing species that would eventually evolve into the ancestors of dinosaurs. These climatic shifts not only influenced life forms, but also affected evolutionary pathways. As environments changed, some species thrived while others faced extinction. This relentless cycle of adaptation and survival laid the groundwork for the age of dinosaurs, demonstrating the profound impact of climate fluctuations on the Earth's evolutionary narrative long before they took their first steps on this dynamic planet. The Paleozoic and Mesozoic eras were times of dramatic change, not just in terms of the evolution of life, but also in climate. Beginning with the Paleozoic era, which spanned from roughly 548 million years ago to 250 million years ago, we saw a range of significant climatic events that shaped our planet. The early Paleozoic was marked by a warm climate, bustling with life in vibrant shallow seas. Toward the middle of this era, around 330 million years ago, the Earth experienced a notable cooling and a moderate glaciation event known as the Late Paleozoic Ice Age. This took place primarily in the southern hemisphere, where large ice sheets formed. As the Paleozoic transitioned into the Mesozoic era, around 250 million years ago, the climate began to warm again dramatically. The Mesozoic, often called the Age of Reptiles, lasted until about 65 million years ago and saw significant climatic fluctuations. The Triassic period started with dry conditions and frequent wildfires, fostering the evolution of many modern plant groups. Following this, in the Jurassic period, the Earth warmed substantially, leading to the establishment of a moist and lush environment. Giant dinosaurs roamed vast forests, and the oceans teemed with life, including the first appearance of marine reptiles. Towards the end of the Mesozoic, conditions began to change significantly once more. The late Cretaceous period experienced a warm climate characterized by high sea levels, resulting in extensive shallow inland seas. This warm and wet climate supported a rich diversity of life, including dinosaurs, but it also set the stage for dramatic shifts as we approached the end of the Mesozoic. The Earth faced significant stress due to volcanic activity and tectonic shifts, which caused further disruptions in climate and ultimately set off events leading to the mass extinction that would erase the dinosaurs. Understanding these climatic events offers a window into how life on Earth has adapted to and evolved in the face of shifting environmental conditions. The lessons from the Paleozoic and Mesozoic eras remind us of the delicate balance within Earth's climate and ecosystems, a balance that continues to be tested to this day. The changing oceans have had a profound impact on life, both in the water and on land throughout Earth's history. A key factor is the ocean's role in regulating the planet's climate. As ocean temperatures rise or fall, they significantly influence weather patterns and affect the distribution of various species. For instance, warmer waters can lead to shifts in marine ecosystems, driving fish and other marine organisms to seek cooler areas. This migratory behavior can ripple through the food web, impacting predators and prey alike. Moreover, rising sea levels can lead to the inundation of coastal habitats, affecting both terrestrial ecosystems and human settlements. Coastal wetlands, for example, serve as vital nurseries for many marine species and act as buffers against storm surges. As these areas become submerged, the ecology changes dramatically, disrupting the life cycles of fish and birds that depend on these habitats for breeding and feeding. Additionally, changes in ocean chemistry, such as increased carbon dioxide absorption, lead to ocean acidification. This can negatively affect calcifying organisms like corals and shellfish, which are crucial components of marine ecosystems. Coral reefs, often called the rainforests of the sea, provide shelter and food for a myriad of species. Their decline can have cascading effects throughout the marine environment, ultimately influencing terrestrial food chains when predators depend on these marine species. Finally, the interplay between ocean life and terrestrial organisms often involves complex relationships. For instance, coastal dolphins and seabirds rely on marine food sources, which are, in turn, influenced by oceanic changes. As marine environments alter due to temperature fluctuations or chemical changes, these relationships may be disrupted. Such changes serve as a reminder that the health of the oceans is inextricably linked to the vitality of life, both in the water and on land, emphasizing the interconnectedness of Earth's ecosystems. The volcanic eruptions have played a significant role in shaping prehistoric climates and ecosystems. When a volcano erupts, it releases vast amounts of ash, sulfur dioxide, and other gases into the atmosphere. These materials can lead to short-term cooling of the Earth's surface. For instance, the ash clouds reflect sunlight back into space, reducing the amount of solar energy that reaches the ground, and this phenomenon can last for months or even years after an eruption. During prehistoric times, one notable example is the eruption of Mount Toba, around 78,000 years ago, which is thought to have caused a dramatic drop in global temperatures and may have triggered a volcanic winter. The cooling effect of volcanic eruptions can disrupt weather patterns, leading to longer and harsher winters and altering rainfall distribution. Such changes can dramatically impact ecosystems. Flora and fauna that thrive in specific temperature and moisture conditions might struggle to survive or reproduce. The eruption's immediate effects can decimate populations of plants and animals, while long-term climate shifts can lead to the extinction of species that cannot adapt quickly enough to a new environment. In contrast, volcanic eruptions also introduce new nutrients to the landscape through their ash. The minerals and elements released can enrich the soil, promoting new plant growth when conditions stabilize. This rebirth can create opportunities for different species to flourish, allowing whole ecosystems to evolve over time. For example, the aftermath of a significant eruption can lead to a rich diversity in the types of vegetation that emerge, which in turn supports a variety of animal life. The legacy of volcanic eruptions is a complex tapestry of destruction and renewal. While they can cause immediate and catastrophic climate changes, they also set the stage for new ecological dynamics to develop. Such events remind us of the Earth's powerful forces and its resilience as life continuously adapts and evolves in response to dramatic environmental shifts. Understanding the effects of these ancient eruptions not only sheds light on our planet's history, but also helps us comprehend the ongoing interactions within our global ecosystem today. Before the age of dinosaurs, fluctuations in sea levels had a profound impact on the Earth's biodiversity. These changes were primarily driven by varying climate conditions, tectonic activity, and the geological processes that shaped our planet. When sea levels rose, oceans would flood coastal areas, creating new habitats in shallow waters. This provided opportunities for various marine life to thrive and diversify. Coral reefs, for instance, could expand into these newly submerged environments, supporting an explosion of life. Conversely, when sea levels dropped, areas that were once underwater became land. This shift could isolate populations of marine organisms, leading to speciation. While some species adapted to survive in these changing environments, others faced the risk of extinction. The desiccation of habitats and the reduction of shallow marine areas caused a selection pressure that drove evolution in creative directions. Those sea level changes were not merely environmental, but also pivotal in shaping the genetic legacy of different species. The impact of these fluctuations extended beyond the oceans, influencing terrestrial ecosystems as well. For instance, as land became exposed or submerged, ecosystems shifted. This dynamic landscape allowed for the migration and interaction of different species over time. Plants adapted to these changing conditions, which, in turn, affected the animals that relied on them for food and shelter. The relationships between species became a complex web, interdependent and constantly evolving in response to their environment. These ancient shifts in sea level and the ensuing biodiversity changes set the stage for the complex ecosystems we recognize today. They highlight the intricate connection between geological processes and life on Earth, illustrating how fluctuations in our planet's features can inspire creativity in the natural world. Even before dinosaurs roamed, these patterns laid the groundwork for future life forms, reminding us of the ever-changing narrative of existence on our home planet. In the early days of life on Earth, roughly 3 billion years ago, organisms faced an array of challenges from their environments. These life forms were remarkably adaptable, employing diverse strategies to thrive in the ever-changing conditions. One of the most fundamental approaches was developing the ability to utilize various energy sources. Some organisms became proficient at harnessing sunlight through photosynthesis, while others learned to consume chemical compounds for energy through processes like chemosynthesis. Another essential survival strategy was to adopt unique reproductive methods. Early life forms maximized their chances of survival by producing a vast number of offspring. For instance, microscopic organisms like bacteria can multiply rapidly, allowing them to occupy different niches within their habitats. This prolific reproduction created a diverse range of genetic variations, equipping some organisms to better resist environmental stresses, such as shifts in temperature or salinity. Nonetheless, survival wasn't solely about reproduction. It also demanded resilience. Many early organisms developed protective structures or specialized traits to endure harsh conditions. Some bacteria could form spores, a dormant state that allows them to withstand extreme heat, desiccation, and even radiation. This ability to enter a form of suspended animation meant they could wait out unfavorable conditions until the environment improved. Additionally, the formation of symbiotic relationships among early life forms was crucial. These partnerships enhanced survival odds by providing mutual benefits. For instance, certain microorganisms formed symbiosis with larger organisms, offering them nutrients in exchange for a suitable habitat. This interconnected web of relationships contributed significantly to the richness of life on Earth, demonstrating that even the simplest of life forms were capable of intricate strategies to survive in a dynamic world. Long before dinosaurs roamed the Earth, a tapestry of symbiotic relationships began to weave itself into the fabric of life on our planet. These connections between different organisms, whether plants teaming up with animals or various creatures aiding one another, evolved as a strategic means for survival and efficiency. They reflect the astonishing adaptability of life when faced with environmental challenges and opportunities. One of the earliest and most significant examples of symbiosis involves the relationship between plants and fungi, known as mycorrhiza. This partnership dates back to around 400 million years ago, during a period when plants were taking their first steps onto land. Fungi helped these early plants absorb essential nutrients from the soil, while the plants, in turn, provided the fungi with carbohydrates produced through photosynthesis. This mutualistic arrangement greatly enhanced plant growth and nutrient uptake, enabling them to thrive in terrestrial ecosystems. Meanwhile, relationships among various animals were also blossoming. For example, some insects began to form mutualistic connections with plants. Nectar-producing flowers attracted pollinators, such as bees, which, in turn, facilitated plant reproduction by transferring pollen from one bloom to another. This crucial interplay set the stage for the vast diversity of flowering plants that would come to dominate ecosystems long before the age of dinosaurs began. In this ancient web of life, symbiotic relationships were not just beneficial, but essential for survival. As organisms learned to rely on one another for nutrition, protection, and reproduction, they laid the groundwork for complex ecosystems that would evolve over millions of years. These interactions not only shaped the prehistoric world, but also influenced the evolutionary paths taken by the ancestors of both plants and animals, paving the way for the magnificent life forms that would eventually reign during the age of dinosaurs. Behavioral adaptations played a remarkable role in shaping interactions among early creatures in the vast tapestry of life as history. The actions and responses of early organisms often determined their survival in an environment filled with challenges. For instance, The development of social behaviors, such as cooperation and group living, allowed early species to better protect themselves from predators. Groups provided safety in numbers and enabled sharing of resources, such as food and shelter. Competition also influenced behavioral adaptations. Early creatures began to demonstrate more strategic interactions, claiming territories and developing specific rituals to establish dominance without direct conflict. This was crucial in reducing energy expenditure and avoiding injuries, which could jeopardize survival. For example, some animals exhibited vibrant displays or specific vocal calls to attract mates or intimidate rivals, highlighting how these behaviors served as evolutionary advantages. Communication, too, was pivotal in these interactions. Early organisms developed various ways to relay important information, whether it was signaling danger, indicating the presence of food, or attracting mates. This evolution of communication opened up new avenues for collaboration and socialization. Consider the complex dances of bees or the songs of birds. These behaviors have profound implications on their communities and ecosystems, cultivating intricate relationships. Ultimately, these behavioral adaptations laid the groundwork for the rich and diverse interactions we see in today's ecosystems. The interplay of cooperation, competition, and communication among early creatures fostered a dynamic network of relationships that continues to evolve. This highlights a crucial understanding. The essence of survival is not merely about physical attributes, but also about how organisms behave and relate to one another in their quest for existence. The evolution of nesting and reproductive strategies among ancient species is a fascinating journey that intertwines environmental pressures, survival needs, and the basic instincts of different organisms. In the early stages of life on Earth, the primary goal for any species was survival. Many ancient organisms, particularly those that lived in water, had relatively simple reproductive strategies. They often released vast numbers of eggs into the environment, hoping that sheer quantity would ensure that some offspring would survive to adulthood. As some species transitioned to land, a shift occurred in their reproductive strategies. Nesting became an essential behavior, driven by the necessity to protect eggs from predators and environmental hazards. Soft-bodied creatures, like amphibians, might choose sites that provided moisture, while reptiles developed hard-shelled eggs, allowing them to lay their eggs in more varied environments. This shift not only enhanced the chances of survival for eggs, but also allowed parents to play a more active role in their offspring's early life. Throughout evolution, different species developed unique nesting strategies that reflected their habitats and lifestyles. For instance, birds, which evolved from small theropod dinosaurs, created intricate nests to keep their eggs safe and to provide warmth. Some species went even further, developing elaborate courtship behaviors to attract mates and ensure that their nesting sites were suitable. This behavioral adaptation was crucial, as it allowed them to successfully rear young in an ever-changing environment. In contrast, many insects adopted alternative strategies, such as laying eggs in protected environments or utilizing parental care to ensure the safety of their young. These diverse approaches to reproduction highlight the interplay between evolution and environmental adaptation over millions of years. As ecosystems changed and new challenges arose, nesting and reproductive strategies continued to evolve, shaping the rich tapestry of life we observe today. Territoriality and social structures played pivotal roles in the survival of early species, especially as they navigated the challenges of their environments. For early mammals and even some reptilian species, claiming a territory meant securing a space rich in vital resources like food, water, and shelter. This was particularly important in ecosystems where competitors or predators were a constant threat. By establishing and defending territories, individuals ensured not only their own survival, but also the survival of their offspring, thereby contributing to the continuation of their species. Additionally, social structures enhanced the viability of early communities. Species that formed groups often exhibited cooperative behaviors, improving their chances of survival. For instance, pack hunting in species like early canines allowed them to bring down larger prey that a lone hunter could not manage. This cooperation extended beyond hunting. Communal care of the young and shared vigilance against predators created a safer environment for raising future generations. Among social animals, hierarchies emerged, influencing individual roles within the group. This social organization allowed for more efficient resource distribution and conflict resolution, which further minimized risk and enhanced survival. By collaborating and forming bonds, early species could adapt to changing conditions, whether faced with climate shifts or the emergence of new competitors in their habitats. Territoriality fostered individual resource protection, while social structures promoted cooperative survival strategies. These two factors combined created a foundation for the evolutionary success of countless species, giving rise to intricate relationships that are still observed in the natural world today. As we look back at our evolutionary history, it becomes clear that these social dynamics were crucial in shaping the future of life on Earth. The Triassic period, spanning from approximately 253 to 249 million years ago, marks a pivotal moment in Earth's history. This period came after the Permian extinction, which was the most catastrophic mass extinction the planet had ever known, wiping out nearly 90% of marine species and 75% of terrestrial ones. As life began to recover, the Triassic offered a unique window where new forms of life emerged. During the Triassic, the Earth's continents were primarily joined together in a single landmass known as Pangaea. This vast expanse provided diverse habitats and environments, fostering the evolution of various species. Among these were the ancestors of dinosaurs, small archosaurs that began to adapt and thrive in this changing ecosystem. These early dinosaurs were relatively small and competed with other reptiles for resources, but they held significant potential for evolutionary growth. Meanwhile, the Triassic period also saw the rise of other important life forms, including the first mammals and the thriving of various plant species such as cycads and conifers. The climate during this time was generally warm and dry, which allowed for the flourishing of different ecosystems. This combination of environmental conditions and evolutionary experimentation created a rich backdrop for the eventual dominance of dinosaurs in the Jurassic period. As the Triassic drew to a close, significant changes began to take shape. A series of extinction events marked the end of this period, paving the way for the Jurassic Age. This transition allowed the dinosaurs to rise as the dominant terrestrial vertebrates, signaling the start of the age we often refer to as the Age of Dinosaurs. The Triassic, therefore, served not just as a transitional phase, but as a crucial foundation upon which this new world would be constructed. Before the grand era of dinosaurs took center stage, a fascinating group of reptiles called archosaurs roamed the Earth. These ancient creatures emerged over 250 million years ago during the late Permian period. The archosaurs included not only the ancestors of dinosaurs, but also those that would later give rise to modern birds and crocodiles, forming a crucial branch on the evolutionary tree. Among the earliest archosaurs were the thecodonts, a diverse group of reptiles that exhibited both bipedal and quadrupedal forms. These creatures were instrumental in pioneering new adaptations that allowed them to thrive in various environments. Their evolution marked a significant turning point as they developed characteristics such as more advanced limb structures and better respiratory systems, which would serve as precursors to the later success of dinosaurs and their relatives. Another notable group within the archosaurs was the proterosuchids, early archosaur forms that lived during the Triassic period. These animals were adept hunters, equipped with sharp teeth and a streamlined body, showcasing the versatility that archosaurs would later be known for. Their presence highlighted the adaptive radiation of archosaurs into numerous ecological niches, setting the stage for the explosive evolution of reptiles, including the mighty dinosaurs. Early archosaurs laid the groundwork for a major evolutionary leap, bringing forth new traits that would dominate terrestrial ecosystems for millions of years. Their legacy continues to echo in today's diverse species, reminding us how the early chapters of life on Earth shaped the very fabric of our planet's biological history. The rise of dinosaurs as the dominant terrestrial creatures on our planet is a story shaped by various environmental pressures that unfolded over millions of years. Beginning around 230 million years ago, during the Triassic period, dinosaurs emerged from a group of reptiles called archosaurs. Their ascendancy coincided with dramatic changes to Earth's climate and ecosystems, which set the stage for their evolutionary success. During this time, about 200 million years ago, the supercontinent Pangaea was breaking apart, leading to a diverse array of habitats. As the continents shifted, they created new environments, which introduced different climate conditions and ecological niches. This rapid environmental change provided dinosaurs with opportunities to exploit resources in ways that other species could not, enabling them to diversify and adapt to various conditions. Their evolutionary traits, like warm-bloodedness and advanced respiratory systems, allowed them to thrive in these shifting ecosystems far better than many of their rivals. Additionally, the end of the Triassic period was marked by a mass extinction event that wiped out many other competing species. This sudden loss of biodiversity allowed dinosaurs, which had already started to dominate as predators and herbivores, to fill the ecological void left behind. With fewer competitors and predators, dinosaurs expanded rapidly, exploring new evolutionary paths, giving rise to some of the most inspiring creatures to ever walk the Earth. As the Jurassic period unfolded, dinosaurs continued to thrive and evolve into a wide variety of forms, from towering sauropods to swift theropods. This adaptability not only made them dominant terrestrial creatures, but also established them as a cornerstone of prehistoric life. The incredible tale of how environmental pressures fostered their rise highlights the intricate interplay between life and a changing Earth, illustrating the resilience and ingenuity of life in the face of transformation. The transition from the Permian to the Jurassic marks a monumental shift in Earth's biological landscape, driven largely by the catastrophic events of the Permian-Triassic extinction. This event, which occurred around 250 million years ago, was the most significant mass extinction in our planet's history, wiping out nearly 90% of all marine species and 75% of terrestrial life. The dramatic loss of biodiversity set the stage for the emergence of new forms of life in the Triassic period. As life began to rebound during the Triassic, the ecosystems started to resemble those we would recognize a bit later. Tropical forests re-emerged, dominated by hardy cycads and ferns, alongside the early ancestors of modern conifers. The land also welcomed a variety of reptiles that took on numerous ecological roles. These were not the great dinosaurs we often think of, but rather smaller, agile creatures. By the end of the Triassic, global conditions were beginning to stabilize, and mammals, although still small, were starting to appear. This period was crucial, as it paved the way for dinosaurs to dominate the Jurassic. The Jurassic, which followed the Triassic, showcased a remarkable diversification of ecosystems. The climate was warm and moist, ideal for the widespread development of lush vegetation. Towering ferns, ginkgo trees, and immense conifers created vast forests that provided habitat for diverse animal species. Not only did the dinosaurs flourish during this era, but new flying reptiles, like pterosaurs, also took to the skies, and marine reptiles thrived in the oceans. This rich tapestry of life was characterized by a seemingly endless variety of shapes and sizes, illustrating nature's remarkable ability to adapt and evolve. As we look back on this transition, we can marvel at the resilience of life and the dynamic processes that shape our planet's biosphere. From the ashes of mass extinctions, complex ecosystems have arisen, reminding us of the interconnectedness of all life forms across time. The story of the Permian to Jurassic transition is not just one of survival, but of the remarkable power of evolution to create and recreate life in countless forms. Paleontologists have a fascinating job piecing together the history of life on Earth, and specifically the origins of dinosaurs. To understand how dinosaurs emerged, they search for various clues, beginning with the fossils of ancient organisms. Fossils are like time capsules, providing tangible evidence of past life forms. By examining these remnants, which can range from bones to footprints, scientists glean insights into the anatomy and behavior of early ancestors that lived millions of years ago. Another important aspect is the geological context of the fossils. The layers of rock where these fossils are found tell a story of Earth's history. Each layer represents a different time period, and by studying the sequence of these layers, paleontologists can establish a timeline of when certain species existed. This helps to map out how life evolved over millions of years, revealing connections between various groups of organisms, including those that eventually led to the first dinosaurs. Additionally, paleontologists analyze the morphology or physical structure of these fossils. By comparing developmental traits over generations, they can identify evolutionary relationships between species. For instance, examining the skeletal structure of early reptiles provides insights into how traits adapted over time, leading to the distinctive features of dinosaurs. This comparative analysis helps scientists trace back through the evolutionary tree. Finally, paleontologists also consider modern species to look for living analogs. Birds are now understood to be descendants of certain dinosaur lineages. By studying their genetics and behaviors, scientists can gain a clearer picture of how certain traits may have developed. All these clues, woven together, form a rich tapestry of life that illustrates the remarkable journey leading to dinosaurs and informs our understanding of evolution as a whole. Before dinosaurs roamed the Earth, our planet was inhabited by a fascinating array of life forms. Fossils from the Paleozoic era, which spans from about 546 million to 250 million years ago, provide a remarkable glimpse into this ancient world. Among the most significant fossils from this period are those of trilobites, which were sea creatures resembling large, armored pill bugs. Their diverse shapes and sizes tell us about the complex ecosystems within the oceans and how life adapted to various conditions. Another key fossil group includes early fish, such as the ancestors of sharks and bony fish. These fossils reveal the transition of life from water to land. Through the study of these creatures, scientists have learned about the evolution of vital features, such as jaws and paired fins, which later became important for land animals. The fossil record also shows the emergence of the first amphibians, illustrating how life began to explore terrestrial environments, marking a critical step in the history of evolution. Moving through this era, we encounter the earliest land plants as well. Fossils of ancient ferns and mosses indicate that our planet was slowly transformed by green life. These plants played an essential role in altering the atmosphere, helping to create conditions more suitable for future animal life. The stories told through these plant fossils reveal important ecological relationships, showcasing how flora and fauna evolved together in a delicate balance. Finally, the Devonian period, also known as the Age of Fish, includes fossils from this time, such as those of the first insects and terrestrial arthropods. They provide hints of ecosystems teeming with life and set the stage for the more complex organisms that would follow. By piecing together these narratives, we gain vital insights into not only the creatures that lived before the dinosaurs, but also the evolutionary processes that led to the incredible diversity of life we see today. Advancements in technology have dramatically reshaped our understanding of prehistoric fossils in recent years. In the past, paleontologists relied heavily on basic tools and observational techniques to piece together the history of life on Earth. The discovery of fossils was often a painstaking process, limited to visual inspection and manual excavation. Nowadays, however, emerging technologies have allowed scientists to delve deeper into the intricate details of these ancient remnants. One of the most significant breakthroughs has been the development of imaging technologies, like computed tomography or CT scanning. This non-invasive method allows researchers to create detailed three-dimensional images of fossils, revealing hidden structures that were previously invisible. With CT scans, paleontologists can examine the internal anatomy of a fossilized skull, for example, without damaging the specimen. This kind of insight has led to new understandings of how prehistoric creatures lived, moved, and interacted with their environments. Additionally, molecular techniques have also played a crucial role in our evolving comprehension of fossils. Scientists can extract ancient DNA from some exceptionally well-preserved specimens, which provides information about the genetic relationships between extinct species and their modern relatives. This genetic data can help clarify the evolutionary pathways that led to the rich tapestry of life we see today. It also opens the door to possibilities, such as understanding how ancient organisms adapted to their changing environments. Lastly, advancements in dating methods, including improved radiometric techniques, have allowed for more accurate timelines of when specific species existed. This means that our chronologies of evolution are becoming clearer and more precise. With these combined technological advancements, our picture of prehistoric life continues to evolve, shedding light on the complexity and diversity of life on Earth long before human existence. Each discovery adds another brushstroke to the vivid mural of our planet's ancient history, inviting us to explore the rich legacy of life that has come before us. Long before dinosaurs roamed the Earth, our planet was alive with a mesmerizing array of life. Some of the most significant fossil discoveries from this ancient time have provided us with a window into a world filled with bizarre creatures and thriving ecosystems. First, we can turn to the Ediacaran biota, discovered in the mid-20th century, which includes soft-bodied organisms that lived approximately 600 million years ago, just before the dawn of the Cambrian period. Fossils like Dickinsonia, with its ribbed, oval shape, suggest that life was evolving in ways we hardly begin to understand. These organisms represent some of the earliest complex life forms, and their very existence challenges our assumptions about the simplicity of life in such ancient times. Then, there is the Cambrian explosion, a remarkable period around 540 million years ago, when life rapidly diversified. Fossils found in places like the Burgess Shale in Canada showcase this explosion. Creatures such as Hallucigenia, with its strange, elongated body and spikes, puzzled scientists for years about its classification. These fossils highlight the immense creativity of evolution, revealing the emergence of many body plans and ecological roles that would not only dominate the oceans, but lay the groundwork for future terrestrial life. In addition to these, the discovery of the first amphibians marked a critical transition from water to land. Fossils from the Devonian period, around 400 million years ago, such as Tiktaalik, illustrate a key evolutionary step with features that allowed it to navigate both aquatic and terrestrial environments. Tiktaalik possesses a flat head and sturdy limbs, embodying the transition that would eventually lead to frogs, reptiles, and mammals. Finally, the Carboniferous period, roughly 360 million years ago, gifted us with an extensive range of fossilized remains, including gigantic insects and lush, swampy forests. The impressive coal deposits formed during that time reveal much about the extensive plant life necessary to support such biodiversity. This period was crucial for laying the foundations of Earth's atmosphere, contributing to the conditions that would allow dinosaurs, and eventually, mammals to flourish. Through these remarkable fossil discoveries, we continue to piece together the rich tapestry of life that existed long before the reign of the dinosaurs. Paleontologists are like detectives of the distant past, using fossils as clues to uncover the mysteries of prehistoric life. When they discover fossil remains, the first step is to analyze their structure. This involves examining the size, shape, and arrangement of bones or shells, which can indicate what type of organism it was. For instance, the distinctive features of a dinosaur femur can tell a researcher whether it belonged to a predator or a herbivore. Similarly, the intricate patterns on a shell may clue them into the animal's habitat and lifestyle. In addition to examining physical characteristics, paleontologists also consider the context in which fossils are found. The layers of rock surrounding a fossil, known as strata, provide valuable information about the age of the fossils. Different layers represent different time periods, often reflecting changes in climate or geological activity. By dating these layers, researchers can place the fossil within a timeline, revealing how life evolved over millions of years. Moreover, paleontologists rely on comparative anatomy, a method where they compare fossils to modern organisms. This can help them identify evolutionary relationships. For example, if a fossilized creature has similar features to a modern bird, scientists may conclude it shares a common ancestor, shedding light on its life history and adaptations. Finally, advanced technologies like computer imaging and isotopic analysis are playing a transformative role in this field. With these tools, paleontologists can create detailed three-dimensional models of fossils, which may reveal hidden features. Isotopic analysis allows them to determine the diets and environments in which these creatures lived, adding another layer of understanding that helps to differentiate various prehistoric life forms. This meticulous and multifaceted approach enables paleontologists to piece together the sprawling tapestry of life that existed long ago. Trace fossils, unlike traditional fossils that preserve the physical remains of organisms, provide invaluable insight into the behaviors and activities of ancient life forms. These fossils include a range of impressions and markings left behind: footprints, burrows, nests, and even feeding marks. By studying these traces, scientists can infer how these creatures moved, what they ate, and how they interacted with their environments. For instance, footprints can reveal a wealth of information about an animal's gait and speed. When researchers discover a series of tracks, they can determine whether the organism was walking or running, and even estimate its size and weight. These traces can also show if the creature was solitary or part of a larger group, indicating social behaviors. Imagine uncovering a pathway of dinosaur footprints, which can hint at herding behavior or pack hunting strategies among these magnificent creatures. Burrows and nests tell another fascinating story. By analyzing the structure and location of these trace fossils, paleontologists can understand the nesting habits of some ancient species, shed light on their parental behaviors, and even discern climate conditions of the time. For example, the detailed study of ancient burrows can reveal whether they were built in soft sediments due to sea level rises or in more stable environments, showcasing how ancient species adapted to their surroundings. Ultimately, trace fossils bridge the gap between the living world and the ancient past, allowing us to reconstruct the life stories of creatures that walked our Earth millions of years ago. Each impression and marking is like a whisper from the past, offering a glimpse into the hidden behaviors and ecological dynamics of ancient organisms, intriguing not just paleontologists, but anyone fascinated by the story of life on our planet. Early ecosystems were complex networks of living organisms interacting with each other and their environment. Long before the age of dinosaurs, these ecosystems, which emerged over 3 billion years ago, primarily consisted of simple microorganisms like bacteria and archaea. These tiny life forms had essential roles, such as decomposing matter and fixing nitrogen, which helped enrich the soil and made it suitable for other life forms. As time progressed, more complex organisms appeared, including algae and, eventually, plants. These early plants were crucial as primary producers, using sunlight to transform energy through the process of photosynthesis. This not only generated oxygen, which dramatically changed the atmosphere, but also created a food source for herbivores, which, in turn, provided energy for carnivorous creatures. In this delicate ballet of life, every organism played a specific role, contributing to the stability and diversity of these ecosystems. With the rise of different species, the interactions among them became increasingly intricate. Predators and prey evolved alongside each other, developing various strategies for survival. Some species became specialized in their feeding habits, while others adapted to unique niches. These adaptations fostered a balance that ensured the persistence of various life forms, allowing them to coexist and thrive within their environments. Early ecosystems were powered by a rich tapestry of species interactions, where each organism contributed to the overall ecological balance. From the simplest microbes to the first green plants, every life form played a fundamental role in shaping the biosphere as we know it today, laying the groundwork for the complex ecosystems that would follow. This interconnectedness echoes through time, reminding us of the delicate balance that sustains our world. Before the astounding age of dinosaurs, the Earth was home to diverse ecosystems brimming with life forms that thrived in different environments. These ecosystems were interconnected through complex food webs that formed the basis of survival for countless species. The food webs varied significantly depending on the time period, but they primarily included a mix of plants, small and medium-sized animals, as well as larger predators that influenced the entire ecology. In the Carboniferous period, around 300 million years ago, vast rainforests flourished. Gigantic ferns, horsetails, and seed ferns dominated the landscape, creating a rich environment for a variety of herbivorous insects and early vertebrates. At the top of the food chain stood formidable amphibians and early reptiles that depended on these plants and herbivores for sustenance. Trophic levels were clearly defined, as energy flowed from the sun to the plants, nourished insects, and thence to larger predators. As we transition into the Permian period, about 250 million years ago, the environment evolved. The extensive swamps of the Carboniferous began to dry, and reptiles diversified. The food webs adapted to include more terrestrial animals, such as the ancestors of mammals and the first true reptiles. The presence of seed plants also expanded the food sources for herbivores, which in turn supported an ever-increasing number of carnivorous species. The complexity of these webs grew, showing us a world rich with interactions and dependencies. The end of the Permian period saw one of the largest mass extinctions, which dramatically reshaped these food webs. However, prior to the rise of dinosaurs, they demonstrate an important narrative of constant change and adaptation. Understanding these ancient webbed relationships helps us appreciate how ecosystems function and evolve, laying the groundwork for the complicated interactions we witness today. They tell a story of survival, competition, and resilience that continues to echo through the ages. The prehistoric era, spanning millions of years, was a dynamic time of interaction between predators and prey. These relationships played a vital role in shaping ecosystems, influencing the evolutionary paths of countless species. At the heart of these interactions were the predator-prey dynamics, which often involved not just the chase and capture, but also remarkable adaptations by both groups. Predators, like the fearsome Tyrannosaurus rex or the agile saber-toothed cat, developed specialized features to enhance their hunting skills. Sharp teeth, powerful limbs, and keen senses allowed them to efficiently track and capture their prey. Meanwhile, prey species evolved an array of survival mechanisms. Some developed physical traits, like hard shells or spines, for protection, while others relied on speed, camouflage, or even herding behaviors to evade their hunters. These adaptations created a fascinating arms race. As one side improved their capabilities, the other had to keep pace or face extinction. Beyond physical adaptations, these interactions also influenced social structures. For example, many herbivores formed large groups to enhance their chances of survival in the face of a predator. Having numbers on their side provided safety. Similarly, predators often relied on pack strategies and cooperation, as seen in wolves or early hominins, to increase their chances of a successful hunt. This intricate interplay of behavior and adaptation showcased the delicate balance of life in prehistoric food webs. The legacy of these interactions extends to modern ecosystems as well. Understanding how ancient predators and prey interacted helps us comprehend the complex relationships that exist today. As we study these prehistoric dynamics, we find not only evidence of survival, but a remarkable story of adaptation and resilience that continues to echo through time, reminding us of the interconnectedness of all living things. In the dramatic chapters of Earth's history, before the dominance of dinosaurs, competition among species played a vital role in shaping ecosystems and spurring diversification. This process took place primarily during the Permian and Triassic periods, when a variety of organisms were competing for resources, like food and habitat. As environmental pressures mounted, those species that adapted to challenges, such as climate fluctuations, predation, and shifting landscapes, began to thrive. One of the primary ways competition drove diversification was through specialization. Species that developed unique traits could exploit different niches, specific roles within an ecosystem. For instance, some early reptiles adapted to life in trees, evolving stronger limbs and a better sense of balance. This branching out into different environments allowed organisms not only to survive, but also to flourish in diverse forms, from nimble climbers to swift ground runners. Consequently, we see the emergence of a variety of body shapes, sizes, and feeding behaviors. Moreover, the relentless competition for survival spurred innovations in reproductive strategies. Some species developed ways to reproduce more effectively, ensuring that their offspring had a better chance of survival in the competitive landscape. This led to an increase in genetic variation and the gradual emergence of new species through evolutionary processes. It was a time of experimentation in form and function, much like a natural laboratory where only the most adaptable and resilient forms could endure. As a result, this pre-dinosaur era was rich with life, populated by an array of plants and animals that laid the groundwork for the flourishing ecosystems that would follow. The adaptations and diversification that arose from competition set the stage for the later explosion of life during the age of dinosaurs, illustrating how the struggle for existence serves as a catalyst for innovation and complexity in nature as grand design. Studying ancient ecosystems offers vital insights into the intricate tapestry of life that shapes our planet today. By examining fossils and sediment layers, scientists can piece together how past organisms interacted with one another and their environments. Understanding these relationships provides a clearer picture of survival and adaptation over millions of years, which is crucial as we navigate the ongoing changes in our modern ecosystems. Ancient habitats reveal patterns of extinction and resilience. For instance, the mass extinctions that occurred throughout Earth's history show us how species respond to sudden changes, such as climate shifts or meteorite impacts. These historical events can serve as cautionary tales, illustrating the potential consequences of habitat destruction and climate change today. As many species currently face extinction, looking back at how life rebounded after past crises can inform conservation efforts and sustainable practices. Moreover, ancient ecosystems also display the diversity of life that once thrived in different conditions, highlighting the adaptability of organisms. For example, the rich veil of life in the lush rainforests of the past reminds us of the importance of biodiversity. Each species plays a role, forming complex interactions that contribute to the health of the entire ecosystem. By recognizing these connections, modern scientists can advocate for preserving biodiversity as a buffer against environmental changes. Finally, the study of ancient ecosystems prompts essential reflections on the future of our planet. The lessons from the past underscore the importance of maintaining ecological balance and protecting vulnerable species. As we face unprecedented global challenges, understanding ancient life can empower us to cultivate a more resilient and diverse biosphere, one that can withstand the tests of time and change. Throughout history, various cultures have offered rich and diverse interpretations and representations of prehistoric life. Many ancient civilizations looked to the natural world around them, including the remnants of prehistoric animals, to inform their myths and artistic expressions. For instance, in some tribal cultures, cave paintings found in places like Lascaux in France depict large mammals, such as woolly mammoths and bison. These images not only served as a record of what these people hunted, but also carried spiritual significance, often representing a connection to the animals and nature. In ancient Egypt, the representation of prehistoric life could be seen in the artistic and religious iconography that intertwined fauna with their belief systems. The ancient Egyptians revered many animals, such as cats and crocodiles, which can be traced back to their ancestors' experiences with similar creatures in prehistoric times. The careful depiction of these animals in statues, tomb paintings, and hieroglyphs shows a cultural legacy that evolved from their understanding of the world around them, reflecting both reverence and practical insights into survival. Moving to ancient China, paleontology formed an integral part of mythology. Fossils discovered in regions like Sichuan are often mistaken for the remains of dragons. This blend of observation and imagination illustrates how prehistoric life influenced cultural narratives. As a result, dragons became powerful symbols in Chinese lore, embodying both the might of nature and the wonders of the unknown, while simultaneously inspiring advancements in science and philosophy over centuries. Today, as our knowledge of prehistoric life expands, these historical interpretations provide profound insights into human thought and creativity. They serve as a bridge, connecting past cultures with the evolving understanding of our planet's history. Embracing the stories told through art myths and early science offers not just a glimpse into how ancient people understood their world, but also a reflection of our continuous quest to decipher the mystery of life that came before ours. Myths and folklore have played a pivotal role in shaping humanity's perceptions of ancient Earth. Long before the advent of scientific inquiry, early cultures relied on stories and oral traditions to explain natural phenomena and their origins. These narratives informed people about their environment, imbued them with meaning, and helped them understand their place in the cosmos. For instance, creation myths, which recount how the world came into being, often reflect the natural landscape and climate of the regions in which they originated, illustrating how intimately people were connected to their surroundings. In many cultures, myths personify elements of nature. The Greeks had gods like Gaia, who represented the earth, and her stories highlighted a reverence for the land and its resources. Similarly, various indigenous cultures feature spirits and deities that embody rivers, mountains, or forests, emphasizing the belief that these features are not just part of the landscape, but integral to their identity and well-being. Such beliefs fostered a sense of stewardship over the environment, as people saw themselves as caretakers of sacred lands rather than mere inhabitants. As societies evolved, these ancient tales influenced how communities interacted with and understood the physical world. Myths served as a guide for agricultural practices, seasonal changes, and even geological events that shaped the Earth's surface, such as volcanic eruptions or floods. These stories often contained valuable lessons, encoded principles that led to sustainable living and harmony with nature. In this way, folklore acted as a bridge, connecting generations, passing down wisdom that encompassed both the mystical and practical aspects of life. Today, studying these myths offers us a window into the thoughts and concerns of ancient peoples. They reveal how humans have always grappled with the unknown, attributing both awe and fear to the forces that govern Earth. As we continue to explore our planet and the universe beyond, These ancient tales remind us of our enduring quest to understand the world around us, merging the realms of science and storytelling in our shared human heritage. The journey of understanding prehistoric life began with early scientific discoveries that laid the groundwork for paleontology and evolutionary biology. The first significant breakthroughs came from researchers in the late 18th and early 19th centuries, who began unearthing fossils in the Earth's layers. These fossils hinted at the existence of creatures long before our time and revealed that life on Earth has undergone dramatic changes through vast stretches of history. One of the earliest figures to delve into these discoveries was the Scottish geologist James Hutton. His theory of deep time emphasized that the Earth is much older than previously believed, which opened the door to consider the complexity of life that existed millions of years ago. Hutton's work laid the foundation for understanding that geological processes we observe today have shaped the planet over immense time spans, a concept that is vital for examining prehistoric life. Another pivotal moment came with the work of scientists like Georges Cuvier, who advocated for extinction based on fossil evidence. Cuvier's studies brought to light the concept that many species that once roamed the Earth are no longer present today. This understanding reshaped how scientists viewed life on Earth. It also sparked a greater interest in studying fossils, leading to the identification of distinctive prehistoric organisms like mammoths and dinosaurs, which captured the imagination of the public and scientists alike. As discoveries continued over the years, additional researchers built upon these foundations. The introduction of the theory of evolution by Charles Darwin in the 19th century further transformed our understanding. Many started to comprehend that life adapts and changes over time through natural selection. This concept not only enhanced our grasp of terrestrial life, but also painted a broader picture of how prehistoric organisms might have lived, evolved, and interacted with their environment, enriching our appreciation for the intricate story of life on Earth. Each discovery in this ongoing narrative invites us to keep exploring the fascinating world of prehistoric life, revealing the mysteries of our planetary past. In contemporary societies, the engagement with prehistoric history is both profound and multifaceted. Society taps into our collective past through various avenues, like archaeological discoveries, popular culture, and education. Museums often play a pivotal role in this engagement, showcasing artifacts and replicas that provide tangible links to our human ancestors. These exhibits invite visitors to step back in time, highlighting how our prehistoric predecessors lived, communicated, and shaped the world around them. Additionally, film and television have become significant mediums for exploring prehistoric themes. Documentaries meticulously recreate ancient landscapes and behaviors based on scientific evidence, helping to visualize a time many millions of years ago. Meanwhile, fictional representations, such as in movies or series set in prehistoric eras, stir the imagination, blending entertainment with elements of reality. These portrayals contribute to a broader public interest in understanding where we come from and how humanity has evolved. Education systems globally integrate prehistoric studies into their curricula. By teaching children about early human societies, their technologies, and their environments, we cultivate a sense of continuity in our heritage. Students learn not only about the survival strategies of our ancestors, but also about their art, culture, and social structures. This foundational knowledge fosters a respect for the past and underscores the importance of learning from our history as we tackle contemporary challenges. Lastly, modern technologies like virtual reality offer even deeper engagements. Such advancements allow individuals to immerse themselves in ancient environments, experiencing life as it may have been eons ago. This blend of innovative technology and prehistoric inquiry invites new generations to explore their past in ways that previous societies could hardly imagine. Through these varied channels, the fascination with prehistoric history continues to thrive, enriching our understanding of humanity's journey through time. Early explorers played a crucial role in unveiling the mysteries of prehistoric fossils and shaping our understanding of Earth as history. From the late 18th through the early 19th centuries, these pioneers set out on expeditions across continents, discovering a plethora of fossils that had lain hidden for eons. Their findings established a foundation for paleontology, the study of ancient life, allowing scientists to piece together the story of life on Earth and its dramatic evolution over millions of years. One notable figure in this adventure was Marion Ning, an English fossil collector who, in the early 19th century, unearthed remarkable specimens along the Jurassic coast in Dorset. Her discoveries included the first complete ichthyosaurus and plesiosaurus skeletons. Ning's meticulous work not only enhanced knowledge of marine reptiles, but also affirmed that species could go extinct, a revolutionary concept at the time. Her contributions broke ground for future paleontologists and transformed public interest in fossils. In addition to individual collectors, early scientific expeditions often included naturalists who documented their findings meticulously. Teams led by explorers like Charles Lyell and Richard Owen cataloged fossils from around the world, establishing chronological sequences in geological strata that corresponded to different time periods in Earth's history. This synergy between exploration and science allowed for the mapping of ancient ecosystems and the identification of evolutionary timelines, providing insights that would take us far beyond mere curiosity about the past. These early explorations not only unearthed physical remnants of ancient life, but also sparked a broader curiosity about humanity's place in the natural world. The stories told through fossils became a vital part of the scientific narrative, challenging the prevailing beliefs of creation and inviting people to reconsider their understanding of life over the ages. Our appreciation of Earth's rich tapestry of life would not be what it is today without the daring, spirit, and keen observations of these early explorers. The story of life on Earth before the age of dinosaurs is a captivating one, full of remarkable discoveries that have shaped our understanding of ancient ecosystems. One of the most significant events in this narrative comes from the study of fossils, particularly those from the period known as the Paleozoic era, which lasted from about 500 million to 250 million years ago. Here, we began to uncover the origins of life as we know it, including the emergence of complex organisms during the Cambrian explosion, a period around 538 million years ago when a vast array of animal life suddenly appeared in the fossil record. Among the intriguing finds from this era are the fossils of trilobites, ancient marine arthropods that flourished in the oceans. Their diverse forms and adaptive features provide crucial insights into early life and the evolutionary processes that allowed species to thrive in varying environments. Additionally, the discovery of early fish fossils, such as those of jawless fish and later jawed fish, has deepened our understanding of vertebrate evolution and the transition from aquatic to terrestrial habitats. As we move through the ages, the Devonian period, often called the Age of Fish, stands out. During this time, roughly 400 million years ago, significant developments occurred, including the first appearances of amphibians. Fossils from this period, such as those of the early vertebrate Tiktaalik, illustrate a pivotal transition from water to land, showcasing adaptations like lungs and limbs, features that would later define life beyond the water's edge. The discovery of these transitional forms not only supports the theory of evolution, but also highlights the complex pathways life has taken to flourish on our planet. Finally, the Permian period, ending approximately 260 million years ago, witnessed the greatest mass extinction in Earth's history. The fossil record provides a glimpse into the life forms that were prevalent before this catastrophic event. The shift from a diverse array of species to a more homogeneous environment afterwards set the stage for the age of dinosaurs. Discovering these changes helps us appreciate the resilience of life, laying a foundational understanding of how ecosystems adapt and evolve over geological time. Through these remarkable finds, we continue to unravel the complex tapestry of pre-dinosaur life, igniting a sense of wonder about our planet's ancient past. Paleontology, the study of ancient life through fossils, has undergone a remarkable evolution since its inception in the early 19th century. Initially, paleontologists were mainly focused on cataloging fossils, trying to understand the history of life on Earth. Over the decades, the field has expanded significantly, incorporating advancements in technology and new scientific disciplines such as geology, biology, and even chemistry. The integration of these fields has allowed scientists to delve deeper into evolutionary relationships, extinction events, and climate changes that have shaped our planet. One of the key figures in the early development of paleontology was Georges Cuvier, a French naturalist who established extinction as a fact by comparing fossilized remains with existing species. His work laid the groundwork for understanding how life forms change over time. Another pivotal figure is Richard Owen, who coined the term dinosaur, highlighting the importance of connecting fossil evidence to modern-day evolutionary theories. Both Cuvier and Owen helped shift paleontology from mere cataloging to a discipline that explored the dynamics of life and extinction. As the field progressed into the 20th century, new discoveries and methodologies revolutionized our understanding of prehistoric life. The advent of radiometric dating techniques allowed paleontologists to accurately date fossils, unlocking the timeline of life on Earth. This era also saw the rise of influential researchers like Jack Horner, known for his studies of dinosaur behavior and social systems, and Stephen Jay Gould, who introduced the concept of punctuated equilibrium, explaining how species can remain relatively unchanged for long periods and then experience rapid shifts. Today, paleontology continues to thrive, fueled by technological advancements such as three-dimensional imaging and genetic analysis of ancient remains. These tools enable scientists to reconstruct ancient ecosystems and better understand the complexities of evolutionary history. As new fossils are uncovered and analyzed, the questions surrounding biodiversity, adaptation, and extinction remain ever more captivating, ensuring that the field will evolve further, continually enriching our understanding of life on Earth. Uncovering and analyzing prehistoric fossils is an intricate process that combines traditional fieldwork with advanced scientific techniques. One of the first stages begins in the field, where paleontologists conduct extensive surveys to identify potential fossil sites. They examine rock formations, soil types, and even geological maps to locate areas likely to have preserved prehistoric remains. Once a promising site is identified, the team meticulously excavates the earth, using tools ranging from brushes for delicate surfaces to chisels and shovels for heavier work. After the fossils are unearthed, the next step is careful cleaning and preservation. Fossils are often fragile, so scientists employ various methods to protect them from damage. This might involve stabilizing them with special adhesives or employing techniques such as plaster jackets to safely transport them. Once in the lab, advanced imaging techniques like X-ray computed tomography can reveal internal structures. This non-destructive approach allows scientists to study bones without damaging them, opening up new avenues for understanding. Furthermore, scientific analysis extends beyond just inspecting the physical traits of fossils. Researchers often utilize techniques such as radiocarbon dating for organic materials to estimate the age of the fossils. Isotope analysis can provide insights into the diets and ecosystems of prehistoric creatures. These methods reveal not just when an organism lived, but also what it ate and how it interacted with its environment. Finally, the results are meticulously documented and published, contributing to the vast tapestry of our understanding of life on Earth. By sharing their findings, scientists invite others to explore the world of prehistoric life. The methodologies employed in studying fossils not only deepen our knowledge of the past, but also inspire curiosity about the evolution of life itself. Public fascination with dinosaurs, has sparked a vibrant interest in the study of early Earth history. It's not just about the colossal creatures that roamed the planet millions of years ago. It's also about understanding the world they inhabited. This zeal has led researchers to gather more information about the ecosystems, environments, and geological processes of the ancient past. The excitement around dinosaurs serves as a gateway, allowing scientists to delve deeper into how our planet has evolved over eons. When museums showcase impressive dinosaur skeletons, or when films bring these ancient beings to life, it captures the imagination of people of all ages. This surge of interest often translates into funding for paleontological research and education initiatives. Cash-strapped institutions find themselves buoyed by donations, allowing them to support projects focused not only on dinosaurs, but also on the broader context of life on Earth, including the geological and climatic conditions that existed when these giants thrived. Moreover, the methodologies developed while researching dinosaurs often benefit other areas of early Earth studies. For example, techniques in dating fossils or reconstructing past climates have been honed through the study of dinosaur remains. Researchers analyze the isotopes found in fossils to uncover details about their diets and habitats, which, in turn, informs us about the Earth's environments during different geological periods. Lastly, the quest to discover new dinosaur species often leads to explorations in previously understudied areas. As paleontologists embark on expeditions in search of new fossils, they also gather valuable geological data, which can provide insights into the changes in climate and continental drift throughout Earth's history. The pursuit of understanding dinosaurs thus becomes intertwined with a broader exploration of the planet's history, making this interest not just a pursuit of prehistoric life, but a journey into the very foundation of Earth itself. Citizen science plays a vital role in advancing our understanding of ancient life by harnessing the collective power of individuals who share a passion for discovery. Often referred to as non-professional scientists, these volunteers contribute valuable data and observations, enriching the research landscape and amplifying the impact of professional scientists. Through various initiatives and projects, they assist in everything from fossil identification to data collection in archaeology and paleontology. One remarkable aspect of citizen science is its ability to cover vast geographical areas and gather large amounts of data beyond what a small number of researchers could manage alone. For instance, enthusiasts might scour local geological sites for fossils, helping to expand the known distributions of ancient species and even finding new ones. Their findings can lead to significant discoveries, often highlighting how diverse and complex ancient ecosystems were. Each fossil unearthed by a citizen scientist can provide insights into the environmental conditions and climate of a time long past. In recent years, digital platforms have facilitated this movement. Online databases allow citizens to upload their findings, share photos, and even collaborate with researchers from around the globe. Programs like these can lead to crowdsourcing efforts to analyze large datasets, decipher patterns, and promote a collaborative spirit. The collective contributions can help fill gaps in our understanding of the evolutionary history of life on Earth, leading to new hypotheses and theories. Furthermore, engaging the public in the process of scientific discovery fosters a deeper appreciation for ancient ecosystems and the history of life. This collective journey not only advances scientific knowledge, but also cultivates a sense of stewardship for our planet. In every fossil or ancient artifact discovered by a citizen scientist, we see the thread connecting us to ancient life, offering a glimpse into the magnificence of our world as past and highlighting the crucial importance of preserving this knowledge for future generations. Before the age of dinosaurs, Earth was home to a rich tapestry of life that paved the way for the spectacular variety of creatures that would later roam the planet. The environment during the Paleozoic era, which lasted from roughly 500 to 250 million years ago, was vastly different from what we recognize today. During this time, life flourished in the oceans, and the land experienced a gradual transformation as plants began to colonize the terrestrial realm. One of the most prominent theories suggests that among the earliest forms of life were microscopic organisms, like bacteria and archaea, which thrived in the primordial seas. These single-celled organisms set the stage for more complex life forms, contributing to the eventual emergence of multicellular organisms during the Cambrian explosion, around 540 million years ago. Life exploded in diversity and complexity. Strange and marvelous creatures, like trilobites and early mollusks, flourished in the oceans, showcasing evolutionary advancements that were pivotal in the development of future life forms. Another theory centers around the development of plants on land. Initially, the Earth was dominated by simple, moss-like plants, but over millions of years, more complex vascular plants evolved. This green revolution altered weather patterns and provided essential habitats. These terrestrial plants not only influenced the atmosphere by increasing oxygen levels, but also gave rise to new animal species that would inhabit these new ecosystems. The evolution of plants laid the groundwork for herbivorous animals, which, in turn, would shape the ecosystems that would later support the great dinosaurs. In contrast to these theories emphasizing the gradual evolution of life, there is a more speculative idea that certain major events, like mass extinctions, played a critical role in shaping life before dinosaurs. The Permian-Triassic extinction, for example, eliminated about 90% of Earth's species and set the stage for the rise of the dinosaurs later on. These theories underscore an evolving narrative on how intricate interactions between organisms and their environments led to the diverse biospheres that preceded the age of dinosaurs, offering a glimpse into the ancient life that once thrived on our planet. Modern evolutionary principles provide a crucial framework for understanding ancient life on Earth. At its core, the theory of evolution explains how species adapt and change over time through processes like natural selection, genetic drift, and mutation. This framework allows scientists to interpret the fossil record and identify how life forms have evolved over millions of years, showcasing transitions and adaptations in response to environmental changes. For instance, when paleontologists uncover ancient fossils, they can identify specific anatomical features that suggest how these organisms might have interacted with their environments or changed over time. By comparing these fossils to modern species, researchers can infer evolutionary relationships and trace back lineages. This comparison not only sheds light on the anatomical and biological changes that have occurred, but also reveals how organisms responded to past climate fluctuations, extinction events, and the rise of new ecosystems. Modern genetic techniques further enrich our understanding of ancient life. By analyzing DNA from ancient remains, scientists can reconstruct evolutionary trees that depict the relationships between extinct and existing species. These genetic insights often confirm or challenge previous ideas based solely on morphology, which is the study of form and structure. This combination of fossil evidence, morphology, and genetics draws a clearer picture of life's history on Earth. The application of evolutionary principles also emphasizes the importance of extinction events, such as the one that led to the extinction of the dinosaurs. Understanding these events through the lens of evolution helps us appreciate the resilience of life and the processes through which new species emerge after mass extinctions. In this way, modern evolutionary theory not only enriches our knowledge of ancient life, but also helps us understand our place within the vast tapestry of life on our planet. Theories of extinction offer us valuable insights into the dynamics of early ecosystems. Understanding how species responded to environmental changes, competition, and predation can illuminate the intricate web of life that existed millions of years ago. For example, when we examine mass extinction events, such as the one that occurred at the end of the Permian period, we find that countless species disappeared. This created a blank canvas in ecological terms, allowing us to study how the surviving species adapted and repopulated the Earth. By studying extinction theories, we can deduce the interconnected relationships among ancient organisms. Early ecosystems were often complex networks, where the extinction of one species could have ripple effects throughout the food chain. This gives us a clearer picture of ecological balance and the roles various organisms played in their environments. The decline or disappearance of dominant species, for instance, often led to adaptive radiation of others, a phenomenon witnessed after the dinosaurs went extinct, allowing mammals to flourish. Moreover, these theories can help us understand resilience in ecosystems. Some species manage to survive drastic environmental shifts, while others do not. Analyzing these patterns helps scientists identify what characteristics contribute to an organism's ability to adapt and thrive, which is crucial for predicting how current ecosystems may respond to modern challenges, such as climate change and habitat loss. The exploration of extinction theories not only enriches our understanding of ancient ecosystems, but also equips us with the knowledge necessary to address ongoing environmental issues. By reflecting on the past, we can draw parallels to today's ecological challenges and make informed decisions for the future of our planet's diverse life forms. The study of geological time offers us a unique window into the vast history of our planet, stretching back nearly 4.6 billion years. This expansive timeline serves as a framework for understanding not only the age of Earth, but also the remarkable transformations it has undergone. By breaking this immense period into manageable segments, known as eons, eras, periods, epochs, and ages, scientists can chart significant events such as continental shifts, volcanic eruptions, and the evolution of life. One of the first concepts to grasp is that geological time is not linear in the way we typically perceive time in our daily lives. While we often think in terms of years or centuries, geological timescales range from millions to billions of years, which can be difficult to comprehend. To grasp this scale, imagine condensing Earth's entire history into a single calendar year. In this scenario, the planet formed around January 1st, while the appearance of modern humans would only take place in the very last seconds of December 31st. This analogy underscores just how recent major events in Earth's history truly are. Moreover, studying geological time involves understanding the processes that have shaped our planet, such as plate tectonics and erosion. These processes occur over unimaginable spans of time, allowing us to interpret rock layers and fossil records that tell the story of Earth's environments and ecosystems. For instance, certain rock formations reveal clues about ancient seas, mountain building events, and even the climates of different eras. This understanding not only informs us about past conditions, but also raises questions about future changes the Earth may face. Geological time is both a tool and a narrative that helps us connect with our planet's deep history. Each slice of this timeline reveals a chapter that contributes to the intricate story of Earth, inviting us to ponder our place within it. As we delve into these ancient records, we come to appreciate not just the age of Earth, but also the dynamic processes that have shaped life and environments over eons, making our planet a truly extraordinary place. Imagining the potential futures following an extinction event today invites both unsettling scenarios and fascinating possibilities. In the immediate aftermath of such an event, one might envision significant disruptions to ecosystems and human societies alike. The loss of even a few key species can trigger a domino effect, where the balance of food chains and ecosystems is upset, leading to widespread ecological collapse. Major cities might be overwhelmed with chaos, as infrastructure falters and essential services struggle to maintain order. The social fabric could fray as communities grapple with loss and uncertainty. But the path forward from an extinction event could also lead to unexpected resilience and innovation. Humans have a remarkable capacity for adaptation. Those who survive might come together, forming cooperative communities that prioritize sustainability and ecological restoration. Innovative technologies might arise that emphasize renewable energy and preserve remaining biodiversity. A new ethos could permeate society, where conservation becomes central to human identity. Nature could become a source of inspiration for rethinking agriculture, urban planning, and resource management. In a more distant future, if life were to recover following an extinction event, we might witness the rise of new species that evolve to fill the ecological niches left vacant. This phenomenon is known as adaptive radiation, where surviving organisms rapidly diversify. This could lead to the emergence of novel ecosystems that are both alien and beautiful, offering new forms of life that may not resemble what we know today. Perhaps millions of years from now, intelligent life could emerge once again, evolving in response to the reshaped planet. Lastly, such an event could prompt a deeper understanding of our impact on the Earth. Societies might reflect on their shared responsibility for stewardship of the planet. This introspective shift could fuel movements dedicated to healing damaged ecosystems and creating a future that respects the intricate interdependence of life. The hypothetical futures after extinction events present both challenges and opportunities, reminding us that while catastrophe can disrupt our existence, it can also propel us toward a more harmonious and enlightened relationship with the natural world. Studying Earth from the time before the rise of dinosaurs is like peering into a vast archive of natural history. This period, which spans millions of years, is marked by significant shifts in climate, atmosphere, and ecosystems. By examining these prehistoric conditions, scientists can unravel the complex interplays between life and the environment. For instance, understanding ancient carbon cycles can illuminate how climate systems have responded to fluctuations in greenhouse gases over geologic time. During the pre-dinosaur era, fluctuations in volcanic activity led to dramatic changes in the atmosphere. These events released enormous amounts of carbon dioxide, igniting warming periods and transforming ecologies. By analyzing fossils and sediment layers, researchers can trace how life adapted to these environmental stresses. This knowledge is directly applicable today as we face similar challenges, often exacerbated by human-driven climate change. Understanding how ancient organisms responded to environmental shifts helps us predict how current species may react to rapid changes. Additionally, the extinction events that occurred prior to the dinosaurs provide insights into ecosystem resilience and recovery. The Permian-Triassic extinction, often called the Great Dying, wiped out a large portion of life on Earth. Studying how ecosystems rebuilt themselves after such catastrophic events reveals the mechanisms that foster resilience. This is vital information today, as conservationists work to protect biodiversity in the face of habitat destruction and loss of species. Finally, lessons from Earth's prehistoric environments remind us of the interconnectedness of all life. The chemical processes that sustained ancient ecosystems are much the same as those we observe today. By learning from the delicate balance of prehistoric ecosystems, we can better understand the footprints we leave behind and the sustainable practices needed to preserve the intricate web of life on our planet. Understanding prehistoric life offers invaluable insights for contemporary conservation efforts. By studying ancient ecosystems and the creatures that inhabited them, scientists can unravel the complex relationships within ecosystems over millions of years. These insights reveal how species adapted to their environments, providing critical lessons on resilience and vulnerability in the face of change. For example, examining extinction events in the past allows researchers to identify patterns that can inform how current species might respond to environmental pressures related to climate change and habitat destruction. Moreover, prehistoric life teaches us about the consequences of biodiversity loss. During various mass extinction events, ecosystems suffered when a significant number of species vanished. This loss disrupted food webs and led to long-lasting impacts on the Earth's biological diversity. By understanding these past events, conservationists can advocate more effectively for protecting existing species as they recognize the interdependence of life. This highlights the urgency of preserving biodiversity today to avoid repeating history. Fossil records also provide clues about how ecosystems recovered from past disasters, information that can guide current conservation strategies. For instance, analyzing the conditions under which species thrived again after an extinction event can help us create more effective restoration plans. These plans can focus on reintroducing species that historically cohabitated or managing habitats in ways that mimic favorable prehistoric conditions. Such approaches acknowledge nature's ability to rebound, but emphasize the need for careful management. The study of prehistoric life is not merely an academic pursuit. It is a vital tool for shaping our conservation practices. By integrating knowledge from ancient ecosystems, we can create informed strategies to protect our precious biodiversity and foster healthier environments. Embracing these lessons equips us with the wisdom needed to ensure that future generations will continue to coexist with a rich tapestry of life. Extinction events, often referred to as mass extinctions, have had a profound and transformative impact on the development of modern ecosystems. These significant events are characterized by a rapid loss of a large number of species in a relatively short period. When we look back through history, we can see that these events have not only shaped the biodiversity of their time, but also set the stage for the ecosystems we recognize today. Each major extinction event, such as the one that famously wiped out the dinosaurs, opened ecological niches that allowed different species to flourish. After the late Cretaceous extinction, for instance, mammals that had previously been small and relatively obscure began to diversify and evolve into prominent land animals. This laid the groundwork for the mammals, including humans, to become the dominant vertebrates on land. The process of diversification that follows an extinction event is often described as an evolutionary explosion, leading to the rise of new species that fill the gaps left by those that disappeared. Furthermore, extinction events can lead to changes in the structure of ecosystems themselves. With the loss of certain species, particularly apex predators or keystone species, the entire food web can be altered. This chain reaction can result in unexpected consequences, such as population booms of certain species that previously had natural predators. For example, in the absence of large herbivores, some plant species may become overly dominant, leading to shifts in vegetation and habitat for other organisms. Today, as we observe ecosystems around the globe, we are witnessing the continuing effects of both past extinctions and current biodiversity. Our environments are a tapestry woven from threads of ancient extinctions and the species that have adapted in their wake. Understanding this history is crucial not only for appreciating our planet's biological legacy, but also for making informed conservation decisions. As we face modern threats to biodiversity, each extinction is a reminder of the fragility of life and the intricate balance that sustains our ecosystems. The legacies of early life forms are woven into the very fabric of the diversity we see in today as species. The origins of life on Earth date back around 3.8 billion years, and from those humble beginnings, certain fundamental traits had persisted through millennia, shaping modern organisms. One of the most striking legacies is the use of DNA as the blueprint for life. This remarkable molecule encodes the genetic instructions essential for the development, functioning, growth, and reproduction of all living things. The shared reliance on DNA indicates a common ancestry among all species alive today. Early life forms, such as simple bacteria, laid the groundwork for more complex biological processes. For instance, photosynthesis, which was first carried out by ancient cyanobacteria, transformed not only these organisms, but also the planet itself. This process uses sunlight to convert carbon dioxide and water into glucose and oxygen, resulting in a significant increase in atmospheric oxygen. This shift not only paved the way for the evolution of higher life forms, but also created an environment in which aerobic organisms could thrive, leading to the vast array of life we know now. Moreover, the evolution of multicellular organisms arose from simpler forms of life through processes like cell specialization and cooperation. Simple colonial organisms eventually led to more complex colonial structures, giving rise to diverse life forms, from corals to dolphins. The cellular structures and functions developed during these early stages laid the groundwork for complex tissues, organs, and ultimately intricate ecosystems, which continue to evolve and adapt today. Lastly, many molecular and biochemical pathways that originated in ancient life forms can still be found in present-day species. Fundamental processes, such as cellular respiration, remain remarkably similar across different organisms. This common heritage reminds us of the interconnectedness of life. As we explore our planet, from the smallest bacteria to the largest whales, we realize we carry a thread that traces back to life's ancient beginnings, revealing an intricate tapestry of evolution that binds us all together. Drawing parallels between past and current evolutionary changes in species reveals the fascinating continuity and adaptability of life on Earth. In the context of evolution, we can look to the historical record, particularly in the fossil record, which provides a timeline of how species have adapted over millions of years. For instance, we can observe that many ancient creatures, like dinosaurs, have successors in birds, demonstrating a lineage of adaptation to changing environments. Today, we are witnessing similar evolutionary processes, particularly in response to rapid environmental changes caused by human activity. Take, for example, the way certain species have evolved to occupy new niches or adapt to urban environments. Pigeons, originally wild birds, have thrived in cities, displaying changes in behavior and coloration that enhance their survival. This is akin to past evolutionary events where species adapted to new conditions, highlighting a constant theme of survival and adaptation. Additionally, looking at antibiotic resistance in bacteria draws a striking parallel to historical evolutionary changes. Just as species adapted over time to environmental pressures in the past, bacteria are now developing resistance to antibiotics as a response to the overuse of such medications. This rapid evolution is a reminder that, while the mechanisms of change remain the same, the speed at which they can occur may vary dramatically in the face of human influence. In both historical and contemporary contexts, we see that evolution is not a linear journey, but a complex tapestry woven from multiple threads of adaptation and survival. As species continue to evolve today, understanding these parallels enriches our appreciation for the intricate and enduring dance of life on our planet. Each evolutionary change tells a story of resilience, reminding us of our shared connection to the natural world and the importance of recognizing and preserving it for future generations. To convey the dramatic history of Earth before dinosaurs, it is essential to employ storytelling techniques that immerse listeners in the vivid landscapes and tumultuous events of that era. One effective technique is the use of vivid imagery, which paints a detailed picture of ancient environments. By describing lush primordial forests, immense oceans teeming with life, and the cataclysmic volcanic eruptions that shaped the planet, listeners can visualize the world as it once was. This approach transforms abstract facts into relatable experiences, allowing the audience to feel a sense of connection to the Earth's distant past. Another powerful narrative device is personification. Bringing geological forces and ancient life forms to life can create an emotional resonance. For instance, envisioning a massive volcano as a slumbering giant awakening can evoke a sense of awe and respect for nature as power. Similarly, highlighting the struggle for survival among prehistoric creatures, from tiny trilobites to gigantic amphibians, helps to humanize these ancient beings, making their stories relatable and engaging. In addition, a chronological storytelling technique that weaves a cohesive timeline can be compelling. Starting from the formation of the Earth about 4.6 billion years ago in progressing through dramatic events such as the rise of single-celled organisms, the emergence of complex life, and the dramatic shifts in climate and geography creates a clear narrative arc. This helps listeners understand the interconnectedness of events leading to the age of dinosaurs, linking moments of chaos and calm in a grand tapestry of life. Lastly, including personal anecdotes or reflections can further enhance the story. When scientists share their excitement upon discovering a new fossil, or the profound impact of a significant geological discovery, it can inspire listeners and spark their imaginations. By incorporating these narrative techniques, the dramatic history of Earth before dinosaurs can truly come alive, captivating audiences and encouraging them to ponder the wonders of our planet's ancient past. Visual storytelling serves as a powerful tool in enhancing our understanding of prehistoric environments. By painting a vivid picture with images, illustrations, or animations, it allows us to grasp the scale and grandeur of ancient landscapes that are no longer visible to the naked eye. For instance, recreations of lush jungles or arid deserts populated by long-extinct creatures can transport viewers back in time, engaging their imaginations and making the past come alive. These visual representations also help to convey complex concepts about ecosystems and the interactions between various species. Through carefully constructed imagery, we can see how big predators might have hunted or how herbivores adapted to their surroundings. By illustrating the relationships in a food web, we are better able to appreciate the balance of life that existed millions of years ago. This not only fosters a deeper understanding of biodiversity, but also highlights the delicate interplay that has long shaped our planet as history. Moreover, visual storytelling can evoke emotions and foster connection, making the distant past feel more relevant to the present. When audiences witness the struggles for survival or the dramatic shifts in climate illustrated through dynamic visuals, they develop a personal stake in the story. This emotional engagement often leads to a greater appreciation of the significance of prehistoric life and how it informs our understanding of current environmental issues. Lastly, technology plays an instrumental role in visual storytelling today. Using virtual reality, for instance, viewers can step into meticulously crafted environments, experiencing them from a first-person perspective. This immersive approach not only enriches our understanding, but also inspires curiosity, encouraging further exploration into the mysteries of Earth's ancient past and the ongoing evolution of life. Sound design plays a pivotal role in crafting immersive experiences, particularly in documentary filmmaking. It goes far beyond just filling silence. It shapes the emotional landscape of a piece. The subtle hum of a distant engine, the soft rustle of leaves in a forest, or the rhythmic pulse of a heartbeat can transport the audience into the heart of a story. By engaging multiple senses, sound design not only complements visuals, but enhances the narrative, allowing viewers to feel as though they are part of the unfolding events. Moreover, the careful layering of ambient sounds can evoke specific emotions and settings. For example, the rush of wind can evoke a sense of freedom and adventure, while a low droning sound might create tension or foreboding. Music also plays an integral role. The choice of instruments, melody, and tempo can influence how a viewer responds emotionally. A delicate piano piece can underscore moments of introspection, while a bold orchestral score might elevate a scene of triumph. In nature documentaries, sound design highlights the intricacies of the environment, bringing life to the visuals and allowing the audience to hear the calls of wildlife or the whispers of the wind. This auditory richness invites viewers to connect more deeply with the subject matter. The sounds of nature become a third character in the story, adding texture and depth that might not be captured through images alone. Ultimately, sound design is a vital ingredient that enriches storytelling. It ensures a multidimensional experience, weaving together visuals and audio to elicit feelings, stimulate imagination, and foster a deeper understanding of the themes explored. By thoughtfully integrating sound, filmmakers can create a profound sense of presence that resonates long after the final credits roll. Incorporating personal stories or anecdotes into a documentary about the ancient past can significantly enrich the narrative and engage the audience on a deeper level. These relatable tales create emotional connections, allowing listeners to envision the lives of those who lived thousands of years ago. By weaving in personal experiences that reflect broader historical themes, filmmakers can illuminate the human side of history, making it more accessible and resonant for the audience. Take, for example, the story of a fictional ancient farmer who relies on the Nile's annual floods for irrigation. Through this character's eyes, viewers can understand the agricultural practices of ancient Egypt while experiencing the anticipation, hope, and challenges that come with farming. These personal narratives serve as a bridge between the present and the past, illustrating that, although times have changed, human emotions and struggles remain quite similar across eras. Another effective approach is to include anecdotes from modern-day descendants of ancient civilizations. These individuals often have stories passed down through generations that reflect the enduring cultural practices, beliefs, or conflicts. By sharing these living histories, the documentary honors the legacy of ancient societies and emphasizes how their impacts still resonate today. Such connections invite audiences to appreciate the continuity of human experience across time. Ultimately, incorporating personal stories enriches the documentary's narrative, encapsulating dry facts within the frame of human experience. This approach not only informs viewers about ancient practices and events, but also evokes a sense of empathy, letting them feel what it might have been like to walk in those ancient footsteps. Through these touching vignettes, the ancient past becomes not just a series of events, but a living tapestry of human life that still influences us today. When it comes to presenting complex scientific concepts to a general audience, one of the most effective formats is the narrative format. Stories have a unique ability to engage people and draw them in. By weaving scientific ideas into compelling narratives, you can make even the most intricate topics more relatable and understandable. For instance, using real-life examples or historical anecdotes allows listeners to see the human side of science, making the information resonate more strongly. Visual aids play an important role as well. Diagrams, animations, and even simple infographics can clarify difficult ideas. A well-crafted visual can enhance understanding by providing a mental image to accompany the verbal explanation. This combination of storytelling and visual support creates a powerful way to present information, as it caters to different learning styles while making complex ideas more digestible for a broader audience. Simple language is crucial. The choice of words can dramatically impact the audience's comprehension. Avoiding technical jargon and using everyday language helps demystify science and brings it into the listener's realm of experience. For example, instead of delving deep into the intricacies of quantum mechanics, one could explain concepts using analogies from daily life, such as comparing quantum particles to fuzzy balls bouncing around a room. These comparisons can spark curiosity and make profound concepts seem more tangible. Finally, interactive elements can enrich the experience. Engaging the audience through questions or discussions encourages active participation and leaves room for exploration. Incorporating demonstrations or even hands-on activities can ignite interest and improve retention. When science is shared in a captivating, relatable way, it not only educates but inspires curiosity about the wonders of the universe, inviting everyone to dig deeper into the fascinating world of scientific inquiry. As we delve into the history of life on Earth, the period preceding the rise of dinosaurs, known as the Paleozoic era, is rich with mysteries waiting to be uncovered. Much of our knowledge focuses heavily on the latter parts of this era, particularly the well-studied Devonian and Permian periods. However, there are earlier epochs, such as the Cambrian and the Silurian, where significant gaps in our understanding persist. Researchers are eager to unravel the complexities of early life forms, environmental conditions, and how they navigated drastic changes long before dinosaurs took center stage. One exciting area of exploration involves the origins of complex multicellular life during the Cambrian explosion, which occurred around 500 million years ago. An unprecedented array of life forms suddenly appeared, yet the reasons behind this biological surge remain partially shrouded in mystery. Discovering more about what environmental factors, like changes in ocean chemistry or climate shifts, might have triggered this evolution could reshape our understanding of life's early chapters. Another field ripe for investigation is ancient ecosystems and their interdependencies. By studying microfossils and sediment samples from earlier periods, scientists can piece together how these ecosystems functioned, what dominated the food web, and how predator and prey relationships evolved. Answers to these questions are not just important for understanding the past. They could offer valuable lessons for modern ecology and conservation. Finally, paleogenomics, the study of ancient DNA genetic information from fossil remains, is paving the way for groundbreaking discoveries. While most ancient DNA comes from the more recent past, newer techniques may allow for the analysis of genetic material from much older life forms. This could illuminate evolutionary pathways and relationships among early organisms, shedding light on how the building blocks of life predate the dinosaurs and set the stage for the flourishing of biodiversity that followed. As these areas of research continue to evolve, they hold the potential to transform our view of Earth's early history in ways we have yet to imagine. As we stand on the brink of exciting advancements in technology, we find ourselves in a unique position to redefine our understanding of ancient Earth and its diverse life forms. Innovations like advanced imaging techniques, powerful computational models, and even artificial intelligence are opening new avenues for discovery. For instance, next-generation imaging technologies can reveal microscopic structures within ancient fossils, offering insights into the biology of creatures that roamed our planet millions of years ago. One remarkable technology being developed is DNA sequencing. With it, scientists can extract and analyze genetic material from ancient samples, even those buried in permafrost or salt. This ability might allow us to piece together evolutionary histories that were previously obscured, unraveling how ancient species adapted to their environments. Imagine rediscovering the genetic blueprints of long-extinct plants and animals, helping us understand not just their biological makeup, but also their interaction with the Earth's changing ecosystems. Moreover, advancements in remote sensing technologies have the potential to transform our exploration of ancient landscapes. By using satellites and drones equipped with sophisticated sensors, researchers can map geological formations and identify previously hidden archaeological sites. These tools can reveal how ancient Earth looked and functioned, creating a clearer picture of the conditions in which early life thrived. This geospatial data can help reconstruct ancient environments and ecosystems, providing context for the organisms that live there. Finally, the integration of artificial intelligence into research allows for the analysis of vast amounts of data at an unprecedented scale. AI can help identify patterns in fossil records or climate data that humans might overlook. By creating simulations of Earth's environmental conditions in the distant past, we can better understand how life adapted to changes, such as ice ages and mass extinctions. Collectively, these technologies not only enrich our knowledge of Earth's ancient past, but also prompt us to reflect on the interconnectedness of life and the ever-evolving planet we inhabit today. As we peer into the future of geology and paleontology, we find ourselves standing at the intersection of technology and scientific discovery. One of the most significant advancements is the integration of artificial intelligence in these fields. Geologists and paleontologists are increasingly turning to AI for analyzing vast quantities of data. Machine learning algorithms can sift through rock formations, fossils, and sediment layers, much faster than a human ever could, identifying patterns and anomalies that could lead to groundbreaking discoveries. Imagine a future where a team can predict the location of fossil beds or pinpoint geological structures simply by inputting regional data into a sophisticated program. Moreover, the use of remote sensing technology promises to transform our understanding of Earth's history. Devices like drones equipped with advanced imaging software are beginning to explore inaccessible areas. This could allow scientists to examine and document geological formations and fossil sites from above, offering a bird's-eye view that reveals details previously obscured by terrain. This approach opens up new possibilities for surveying remote landscapes, especially in places where traditional fieldwork is challenging or dangerous. The evolution of collaborative research across disciplines is another transformative trend. Geology and paleontology are increasingly intersecting with genetics, ecology, and climate science. By working together, scientists can create a more holistic picture of Earth's past and its ecosystems. This interdisciplinary approach will help us not only understand how life evolved, but also how geological events influenced these changes over time, advancing our knowledge of Earth's history and its future. Finally, as our awareness of climate change grows, geology and paleontology will likely play crucial roles in informing conservation efforts. By studying ancient climates and extinction events, researchers can better model current ecological changes and predict future trends. The insights gained from past geological and biological shifts will arm us with knowledge that can guide environmental policy and stewardship of our planet. As we move into the coming decades, the synergy of technology, interdisciplinary collaboration, and a commitment to understanding our planet's past will undoubtedly enrich both geology and paleontology, unlocking mysteries that have lingered for millennia. Collaboration across various scientific disciplines can unlock new understandings of prehistoric life by combining different areas of expertise to create a more comprehensive picture. For example, paleontology focuses on dinosaur fossils, while geology studies rock formations and the conditions under which those fossils were formed. By connecting these fields, scientists can better interpret the environmental context in which ancient creatures lived, understanding not just what they looked like, but also how they interacted with their surroundings. Moreover, advancements in technology offer exciting new tools that can enhance our investigation of prehistoric life. Techniques from molecular biology, such as DNA analysis, can be employed alongside traditional fossil studies to uncover genetic relationships between ancient species and their modern descendants. This interdisciplinary approach can reveal evolutionary pathways and adaptations that might otherwise remain hidden if solely examined through a single lens. Even the humanities play a vital role in this collaboration. Archaeologists can work with anthropologists and historians to piece together the behavior and cultures of early humans. By combining archaeological findings with modern cultural studies, researchers can gain insights into how prehistoric communities made decisions, crafted tools, and interacted with the environment, enriching our narrative of human history. Ultimately, this melding of perspectives fosters innovation. Each discipline invites new questioning and alternative methods of thinking about the past. As insights from various fields intersect, they create a richer, multi-layered understanding of prehistoric life, allowing us to appreciate not only the creatures that roamed the earth long ago, but the intricate dynamics of the ecosystems they inhabited. The interplay of these diverse fields fuels curiosity and drives research forward, leading to groundbreaking discoveries that continually reshape our understanding of the past. As we delve deeper into the mysteries of Earth prior to the age of dinosaurs, a host of intriguing questions emerge. One of the fundamental inquiries revolves around the conditions that prevailed during the vast stretches of time before the rise of these iconic reptiles. What did the Earth's ecosystems look like? How did life adapt and evolve in this unique prehistoric environment? The more we uncover about ancient life forms and their habitats from millions of years ago, the more complex and nuanced our understanding of evolutionary history becomes. Research has revealed that Earth's history is marked by significant events, such as mass extinctions and continental shifts. These moments have shaped the planet's biodiversity and climate. Therefore, scholars are asking how these geological and biological transformations influence the trajectory of life leading up to the age of dinosaurs. For instance, understanding the climate conditions of the Permian period, just before the dinosaurs appeared, can provide insights into how life rebounded after one of Earth's most catastrophic extinction events. Furthermore, as we investigate the remnants of ancient habitats, we also ponder how these environments interacted with the atmosphere, oceans, and even space weather phenomena. Did early life forms influence Earth's atmosphere as we know it today? How did microbial life contribute to the planet's conditions centuries before the appearance of more complex organisms? Questions like these not only highlight how interconnected life is with its environment, but also spur new research avenues that connect biology, geology, and climate science. As we gather more data through fossil records and advanced technology, the implications for future research are profound. Scientists can employ this knowledge to predict how current ecosystems may respond to change. By understanding past patterns of evolution and extinction, researchers can draw parallels to today's rapidly changing world, informing conservation efforts to protect our planet's biodiversity. With every new discovery, the quest to understand Earth before the dinosaurs enriches our awareness of life's resilience and adaptability over eons and holds valuable lessons for the future.